All right. Good morning. So I think we'll get started, although because the first talk is online, so there's no need to delay colleagues who are way ahead of us in the time zone. So welcome, Andrew and Akbar. And if you could kindly share your screen and also unmute yourself. And that way we can get started.
Hello, everyone. Nice to be here. My name is Akbar.
Andrew is here. Second.
Did you hear us?
Another second. Yeah, just give us another second.
Yeah.
And is this? Just give us a second.
Oh, did I see Martin there? And Steve?
Yes, Martin's here. There's Michael Rowe. There's Steve Ruff. Everybody's here.
Yes, he is there. Wow.
And,
hi.
Yeah, they can see you from there.
Hey.
Nowhere to hide.
Sorry I couldn't make it, but next time I promise I'll be there. We'll be there next time.
Okay, yeah, great. We're just restarting the system once. There's always a technical glitch, and that good thing it's at the beginning of the session.
That's fine.
We are back again. Dr. Ramzani, could you share your screen, please? And you're muted, so.
Yep, so you can hear us. Dr.
Yeah, I
Akbar
can
is
hear
just...
you now. I can hear you now. You could just share the screen.
Okay. Okay, and let's do that.
Yes, we are able to see your screen. If you could just go to the full screen mode, and I'm going to shut my mic off, so that way you can get started in 30 seconds.
Okay, are you seeing the full screen now? Are you seeing the full screen now?
Yeah, we can see.
Yeah. Okay. Yeah. All right. So we'll start in the next 30 or 20 seconds. Okay. The live streaming on YouTube. So right, I guess. Okay. Okay, we're going to start now. Hi, my name is Andrew Ang. I'm an associate professor here at Swinburne. Today is a joint presentation. I'll take about 5 minutes, and then after that, Professor Akbar will come in and deliver our work on astrometallurgy. So, as I mentioned, we're from Australia, Swinburne, and it's a customary tradition that we actually acknowledge the lands on which we do our research, the Wurundjeri people of the Kulin Nation. We are located in Melbourne, about 5 kilometers away from the MCG for those that like cricket. So the land belongs to the Wurundjeri people of the Kulin Nation. I'm actually together with Rebecca. We are both the co-directors of the Space Technology Industry Institute at Swinburne. We've been established for close to 7 years already. And what we do, our institute is very outward facing in trying to raise the frontiers in astrophysics, aerospace, aviation, and so on and so forth. We have many programs, and today you'll be hearing from one of our superstars in the in the regolith processing, the Institute Regolith Processing, Professor Akbar. You can see here we have programs in AI for space, microgravity, space instrumentation, extraterrestrial resource processing, space robotics, and manufacturing, and so on and so forth. So, if you have any sort of queries and all that, my email is there, Rebecca's email is there. Please feel free to reach out to us. We'll make sure that the sort of courtesy packed slide will reach Professor Chakrabarty shortly after this. Oh, forgot about to thank the organizers for allowing us to speak. Thank you very much, and I hope you find our talk interesting. We do a lot of work with various companies. We are part of the Australian Lunar Rover team, the ROVER team, which is sending the part of the Artemis mission, sending the rover up in the later century of the year, of the decade. And we work on both, the rover technology, radiation for the electronics, shielding for the electronics, and also coatings to make the rover last longer. We also have been working with satellite companies such as Elarostat from Gilmore Space, providing structural parts and also various technology for them to launch their set. I think late last year they launched their satellite. We also do quite a bit of work with other companies such as Hypersonics or rocket technology. So Hypersonics launched last month in the US, and some of our coatings and some of our products or our technologies found in there. So we do quite a bit of work on both sort of the industrial collaboration side and trying to help companies scale and also build TRL across the value chain of the space industry here in Australia. So this is sort of a brief overview about what the Space Technology Institute does. I said I'll be only like less than 5 minutes. So at this point in time, I'd like to hand over the mic to Professor Akbar, who will share his research about astrometallurgy, but also provide a bit of background about what Swinburne is doing in this area. Professor Akbar, please. We can switch over now, please.
Thank you very much, Andrew, for opening the presentation. Also, I'm sorry we couldn't be there, but yeah, it's an honor for us to be able to speak in front of you. So my name is Akbar Ramdhani. One of the professors here in the School of Engineering in Swinburne University of Technology. My expertise is in metallurgy, extractive metallurgy, but I apply my knowledge in the context of extraterrestrial, and we coined the term astrometallurgy. So that's what I'm going to talk about today. Just a bit about acknowledgement to co-authors, co-investigators in the topics that I'm presenting today. So we have Dr. Dedina Baban, Dr. Matthew Shaw, and Dr. Matthew Humbert. So when we started this journey about 5 years ago, they actually my PhD students, and we started this research, and there's a bit of history as well. So after we started this research, this is actually the Mars metal extraction is not their topics for PhD, but after Dedi finished his doctorate, he actually went to CSIRO, National Lab in Australia, actually working in the Mars metal processing. That's why when we started to collaborate with CSIRO, working on this area, and we still doing that until now. But after Dedi finished at CSIRO, he joined Argonne National Laboratory, so he's in USA at the moment. Now Matthew, also Swinburne alumni, he went to CSIRO to work on also in space area, but he comes back to Swinburne, and we will get to have him back actually.
Yes, recent.
Yeah, recent. And Matthew, he was also helping initially with the Mars work, but he's now in the USA. Now, the person that I'm collaborating closely in this area is John Professor Mark Ponsonby from CSIRO. Right, so the context of the discussion is metal processing in Mars, or metal extraction in Mars. The basis, of course, is ISRU, that is in situ resource utilization. So this figure showing one of the reasons why we want to do that. Obviously, bringing stuff from Earth is very expensive. So this is just comparison here. A water bottle costs $1 on Earth, but it's 65,000 on Mars. So if you want to bring that to Mars, for example, so which means that we will need to utilize resources in Mars, but also on the Moon as well as a stepping stone, for example. So that's the basis of this work. So I'm going to talk about metal extraction on Mars, right? So it's a beautiful planet, and red planet, and so if we want to live over there, obviously we need oxygen, food and fuel, right? But also we need to have some infrastructure to make it happen. So we need metals. We need materials that act as a structural materials. So metal is one of them. So we want to make metals on Mars. So how can we make metals on Mars? So let's look at the situation. Obviously, in Mars we have one point is we can bring the metal from Earth, steel bar, whatever. But as I mentioned earlier, it's going to be very costly, obviously. Second, we can also do the ISRU, right? First, we know we have Mars regolith, right? Which contain elements that we can extract. So we can utilize regolith to make metals. We also know that in the Mars atmosphere we have CO2. It means there is a source of reductant. There is a source of carbon, right? So that's something that is different, completely different compared to, let's say, lunar. Right? So when we think about metal making in the context of lunar, then we have to think something that can be done without reductant carbon. Right? But in this case, we have carbon, so that's a good thing. And the other one is the energy. Now, the energy can be coming from solar, right? So that's good. So basically, we combine the solar, CO2, and regolith, and try to make metal from this. Okay. Oops. Right. So let's go into a bit more detail here. So as I mentioned, we have carbon dioxide in Mars atmosphere. And if you look at in more details, table 1 here is showing the typical of general concentration of gases in the Martian atmosphere. And you can see about 95% of the gas is actually CO2. We have about 2.7% nitrogen and other sort of other gases in there as well. So we have 95% CO2, which is pretty good. Second, the regolith. So we go into the regolith here. What is the composition of regolith? So this is some example of typical composition or average composition from the rockness, and this is presented as oxide. Obviously, the actual phases is not oxide. Yeah, we will see in a bit. But if we express it in terms of oxide, we can see that these are the typical composition. In here, you can see mainly it contains silica, 43%, but we also have FeO, right? That's about 19%. So potentially we have we have iron source in there that we can extract. But also there are other things that exist, such as sodium oxide, potassium oxide, and chromium oxide. Yeah, let's go. Next slide. Right. So that's we look at the atmosphere. We look at the regolith. So and then what can we do with the atmosphere? So for those of you who knows, there is this process or reactor called MOXIE. So this is actually in the rover on Mars. So the MOXIE reactor is actually to process the Mars atmosphere, right, the gas CO2, to form oxygen. So it follows an electrolysis process, and this is the general reaction. So 2 CO2 from the gas from the atmosphere, you electrolyze it to form CO and oxygen. Right? Obviously, you want to take the oxygen, but we have the CO. So, so this is something that we can utilize. So we can utilize CO as a gas as a reductant, or we can convert the CO into carbon. Now, the process itself, the electrolysis process itself, if you operate it at higher voltage, you can actually directly produce carbon. There's a carbon deposition. Or in another way to produce carbon is if you sort of condense, this is quite high temperature, condense the CO or lower down the temperature for the CO to form carbon and CO2. So this is quite a common reaction called the Woodward reaction. So you can actually make carbon, solid carbon, but also you can utilize the CO as a gas. So we have the ingredients there. So when we think about this about 5 years ago, 4 years ago, then we tried to sort of to distill it out, to make it into a paper, and we did that and provide the concept. So we've got this one published on metal synthesis on Mars through carbon thermal reduction. So we really think that the use of carbon is one of the easiest way that we can do in Mars. So there is no problem of CO2 emission, of course, in Mars. But yeah, so I think that's the easiest point. So this is the idea. When we have the MOXIE process, it takes CO2 from the atmosphere. Right? The process itself is carried out at 800 degrees Celsius. You get the oxygen for life support, whatever, storage, and we put it in storage. And you can also get the CO2 from the from the process after reduction. But the CO from the process is actually condensed or reduced down to temperature to make carbon and CO2. So CO2 can be returned back into the MOXIE process. Right, so we have this CO-rich gas. At the same time, we use that carbon to make a pellet. Now, don't tell me why at the moment, but I assume it's going to be like a robot doing that. But to make a pellet of regolith with carbon, which are preheated using the heat from CO gas before it goes into the actual reactor for reduction. Right? And we did some thermodynamic analysis, and we proposed this sort of condition here, 1120 degrees Celsius, and at the Mars Martian pressure, so that's 7 millibar. Obviously, we mentioned about a source of energy, which is solar, so we can use solar concentrator or electricity from PV cell, for example. So I should mention Swinburne also has an iconic facilities where we have a solar concentrator. So we use these hot metal halide lamps. 7 of them focus the light into a furnace, and that each of the lamp is 7,000 watt. So you can actually go up to temperature 2,000 degrees Celsius with this concentrated solar. Right, this is just some of the thermodynamic assessment that we did, showing the distribution of iron. So for example, iron, so A is iron in the minerals, B here is iron in solid alloy, and C is iron in liquid alloy, and D is iron in the slag that is lost into the slag. And you can see, let's just choose the red one, which is 6 grams of carbon, right? So we can get a lot of liquid iron if the process is carried out at above 1100 degrees Celsius, as shown in here. I think it's also really good to get into liquid state for easy separation between the iron and the other solid material. Then, so the first publication that we did is about thermodynamic modeling and the concept. Then we want to do the experiment. So we using the actual, not the actual, using Mars regolith simulant. So first we analyze the Mars regolith simulant, characterize it really well to understand what's inside, and to get an actual composition that we can use. So we redo the thermodynamic calculation to optimize the process again. Then we do experimental work, so to demonstrate. So so from this work, for example, the simulant that we use is shown in here. So MGS1 comparison with composition of roughness example. So it's slightly different, but in a way it's close enough, right? So so we use that MGS composition there, and this is the shape of the regolith. So it's very sort of sharp edges, and mainly it's a silicate-based minerals. We also did the EPMA, and you can see from here, mainly this is the initial materials. So mainly it's pyroxenes, a lot of green stuff there, and also feldspar, and other sort of small other phases there. And there's also a small amount of iron oxide in there. If we were to put the composition in terms of the phases itself, about 35% is plagioclase, 22% is olivine, 18% is pyroxene. Iron oxide itself is 6.72, As you can see from here, iron is actually present in many of these phases. So in the form of iron oxide, it's only 6%, it's quite a small amount, but mainly is embedded within the silicate materials. So olivine and also the other sort of mainly olivine basically. So and for those of you who understand about the metallurgy, for example, to extract metals from oxide is much easier than from silicate because it's a different situation. So once we understand about the materials, then we do the experiments. So this is the result of the experiments, and it also has been published. And we did the experiments in the lab, in our lab, at Mars pressure. We mix the MGS simulant with graphite and then heat it at different temperature. In this case, obviously we did not introduce the lower gravity effect. We're going to do that maybe later on. This is a starting point from the chemistry aspect. So this is some of the result from 1000 to 1250 or 1000 to 1450. So basically we can divide it into three sort of region. One is where solid state reduction is dominant between 1000 to 1250. As you can see, more and more bright dots, which is metallic phases, started to form, but it's very small and it's spread out. And then there's a region where we have a partial smelting reduction, that's between 1350 to 1350, sorry, 1300 to 1350, and a full smelting reduction region that is beyond 1400. And when you have full smelting, then this is where the full separation of iron and iron silicon alloy can be done. This is just a comparison between our thermodynamic assessment with experimental result. Some of them is actually similar or same, but obviously there are some kinetic aspect that involved in here, and some of the result is not the same between the experimental and the thermodynamic assessment. So for example, in this case, what you can see in here, liquid alloy also has been predicted to form as low as 1000, right, by thermodynamics, but from experimental result, that's basically happened above that temperature because of that reason, including kinetic reason. This is some of the result after reduction. So this is at 1000. You can see that one small bit here, but that's magnified here. The purple one is iron oxide, the red one is iron. So obviously there's some reduction happen. And D, E, and F also showing some other sort of particles where you have FeO, and iron is actually growing from that FeO. At 1200, so more and more metal produced. So you can see here on, let's say on C, there's a yellow dots. So that is, and also there's a pink dot. So basically the yellow dot, they are metal, iron, but with significant amount of silicon. So it is actually iron alloy with some iron silicon intermetallics inside. Now the purple one is iron with some silicon dissolved in it. So a small amount of that as well. So if you cut the cross section, you can see the inside, something like that, which showing this different sort of phases in that iron silicon alloy with low and high concentration of silicon in it. At 1300, same thing here. You have more and more iron silicon alloy. As you can see from this bigger and much more dots in the microstructure, but also some form of glass silica formation as well, separation of SiO2 from other phases, which is in in the right, so sort of in light or white phases in here, which is quite interesting. 1400, at 1400, as I mentioned earlier, it's a full smelting condition where the iron silicon alloy is melted and then separated from the other solid particle as a separate phase. So this is an example of that iron silicon alloy. This is the round edges there, which is a droplet basically, indicating it was melting at the temperature. But if you look at more details, you can see it's quite a complex dual phase sort of iron silicon alloy material. Right, just a quick one. The phase composition after reduction summarized in this table, and you can see, the silicate is very hard to reduce at a lower temperature, 1000 for example. But as we go into a higher temperature, then you form this glassy materials, but also you form metallic product. In this case, 1400 here. Yes. So, in summary, we think that carbon-thermal reduction of Martian regolith would be the easiest way to start with if you want to make metals on Mars. And we propose a flow sheet that involves cooling of hot CO gas from MOXIE to produce carbon. So what we have in mind is, when you have this oxygen plant or MOXIE in the larger scale on Mars, we will have this steel plant next to it because we will need the CO gas from MOXIE and also to make pellet in that, so in that area. So thermodynamic assessment experimental result demonstrated that the reduction of oxide silicate content in MGS could take place at about 1055 using graphite. If we go above 1400, then it's going to be in the smelting stage where we can separate the iron from the other solid material. So we still have a project currently ongoing to continue this work. So there's one PhD looking at, we're still working with CSR to develop this further. So Muhammad Iqbal is actually working on two things. One is metallothermic reduction of Mars regolith or Mars regolith simulant, but also trying to how we can actually incorporate this effect of low gravity in the experiment. So hopefully we can get updates in the next sort of symposium. So that's basically from me, but I also would like to mention a bit here. So we are quite often to give international course and workshop. So this is an example of that. So we actually gave this course on metallurgy on extraterrestrial planets last year in KIGAM. So KIGAM is a Korea Institute of Geoscience and Mineral Resources. So this particular workshop is 4 days. One of the feedback for this is too long, so maybe next one we're doing this in 2 days. So this interest from our Indian friends, we can actually also give this sort of more detailed courses in this area. I think that's basically from me. So I return back to the moderator. Thank you very much.
Thank you, Professor Ramdhani, Professor Rang. Do we have any questions? Quick.
Hi, this is Steve Ruff.
Hello.
Yeah, so I'm curious about whether you've modeled solar energy concentration at Mars. I'm guessing, well, I don't know if you were just using Earth as an example, but the question really is solar concentration more efficient in terms of the resources that you'd have to install to do solar concentration at Mars versus photovoltaic energy for electrical, processing? So have you modeled that?
Yeah. So we thank you for the question. We haven't modeled it, we haven't modeled it. Obviously, the solar installation in Mars is much smaller compared to Earth, roughly about half. So the temperature that we are aiming for is high temperature between 1,000 to 1,400. So in our lab, we can do that quite easily by concentrating the solar lights. But I haven't got a clue in the actual Mars situation. We haven't modeled it yet, to be honest. But that's quite an interesting question. Obviously, using electricity from solar panel, there's another option there. But I would think that one is for a lower temperature, for example, heating up, preheating of a pellet, for example, or other sort of preheating process. So, so that's my thinking. Yeah.
Thanks.
There was a question from the online audience, and that says, what is the size of the sample that is heated, and how much time is the total experiment?
Yes, so the size of the sample that is heated. So we have I don't remember off the top of my head, but basically we basically ground the lunar regolith into a certain dimension. So it's given in the paper. I think it's about 100 micron, and then we make into a pellet. And the size of the pellet itself is between 1 to 3 grams. So it's quite small. Pick of your small, like size of your nails there. So, but 2 centimeters in diameter, and then thickness is half a centimeters to 1 centimeter. It's quite a small sample. And how much time is the total experiment? So we did a number of different time, but most of the result that I presented there, that is a 2 hours experiment. So that's a 2 hours heating.
Thanks. There's one more question, I think it was there.
Hi, Akbar. It's Martin Van Kranendonk talking. Given the prevalence of, polymers and lightweight, strong materials like carbon fiber, what is the absolute requirement for metals? Like, what are you thinking that metals are going to be used for on Mars?
Yeah, so mainly for structural purposes, like bar for building, something like that. Obviously, you have these lightweight materials or non-metals materials, but I would assume that to process that or making that on Mars will be more difficult. I assume that's not my field. And with metals, it's very abundant. The source of regolith is very abundant, and it's quite a simple process. So I think also on Earth, why we use iron is because it's easier to make and also easy to recycle as well. So I think we still need metals, obviously for a very specific application that requires lightweight, then we use other materials. Yeah.
But there's still a whole process of manufacturing, and once you get the metal, that's still just a rough product. That's not a created metal bar. It just seems like it's an incredibly complex, expensive process to do, whereas you could transport much lighter weight materials and it's just a question. I mean, there will definitely be requirements for metals, but I'm wondering if like structural beams are the actual,
I think it can work at the beginning, but when we go like in a bigger scale and more development, then that's when we will do more in situ resource utilization. So for example, at the beginning, we can actually bring some stuff like the materials from the moon, for example, or from Earth. But once it's getting bigger, then we have to do something more over there.
All right, thank you.
I am very quick in terms of asking two questions to you. One is that what is the heterogeneity in terms of iron concentration?
So
if you think of all the regoliths, what's the kind of heterogeneity in terms of iron concentration? Is it very consistent? There is a large variability, or what is known?
There's a large variability. I don't remember on top of my head, but yeah, it's between 5% to 10%, basically. I don't know that. Maybe there are other people who knows much better.
I can actually address that. So the rock nest that you pointed out was literally, it's aeolian, it's wind-blown sand of a particular particle size, a couple hundred microns. What we do know from all of the different landing sites is that particular material, wind-blown sand on Mars of a couple hundred microns, actually is a globally homogeneous material. So it's remarkably uniform of that particular stuff. The rocks can be highly variable, but that wind-blown, globally homogenized sand is very uniform.
That's nice. And my second question is that you have another mineral which is lying there, which is siderite, which may be much more easy in terms of doing metallurgy compared to using the regolith. What do you think about it?
Yeah, obviously, we can also apply the same concept to that minerals. So it's more about trying to optimize like the amount of carbon, for example, and the temperature. But yeah, it's any iron containing resources would be potentially can be reduced. Siderite, the silicate, the iron oxide as well. So yeah, so that also can be processed as well.
Hi, one quick question. What's the impact, or rather the known impact of radiation on metals or mineralogy as a whole, given the dosage is quite high?
Now, unfortunately, I don't. It's not my field in that one. So, I think for metal, maybe not significantly affect the metal properties. But obviously for human, it will be so I'm guessing, a scientific guess, I don't think it's significantly affecting the performance of metals, the properties of metals, for example. And yeah, that's my.
Just to add on, like, if you're using metals for as structures, of course, the secondary radiation is a issue for humans around. So we'll have to choose accordingly that the secondaries are also suppressed. But otherwise, as such, for the structures, are not going to have any degradation or anything like that. Same with the moon, right? So, yeah.
All right, thank you again, Professor Ramdhani and Professor Ang. We will now move on to the next presentation, which is an in-person presentation shared by Shubham Sharkar and Netra Pillai. Shubham is the person who has been copied to all the emails, so he's been doing a lot of work. So over to you, Shubham and Netra.
Hello, am I audible at the back? Okay, thank you. So good morning, everyone. I will walk you through our journey, like as a whole humankind's journey through ages in the subject of Mars exploration. Okay, so as the idea of this workshop is to be giving a general idea to a wider audience who are not working particularly on the Mars science also. So we'll be very much superficially, we'll be covering all the major highlights so far in terms of exploration strategies and major scientific advancements. And later on, obviously, we'll be discussing some of our recent spectroscopic-based findings. Okay. Not working. Let's use this. So, human beings have been watching Mars in the night sky since ages, and the ancient astronomers, they interpreted this retrograde motion of Mars in the second millennium before the Common Era. And on the 8th century BCE, ancient Babylonian astronomers, they exactly calculated the time of this retrogradation loop, that is 2.1 years. Okay, but things changed and we moved forward with science, and some interesting discoveries and related misconceptions about Mars and related alien life was described by Professor Ruff in the as the very first talk of this conference. That is on YouTube. If you have missed it, you can still watch. Okay, so I'm jumping. After 1960, this is a family portrait, as NASA has said about this image, of all the Mars missions that has ever been attempted. Okay, and as Indian, I feel proud to share the joy of sharing this MOM mission, the 41st of that line, and India's first interplanetary journey. Now, to start with, the initial phases from 1960 to 1965, it was a bit of heckle, okay, marked by some launch failures and then the communicational loss for Mars 1 from the Soviet side. And Mariner 3 also had some mechanical issue during the deployment, but that was quickly recovered in the Mariner 4 that tested the first successful flyby. Okay. So speaking of Mariner 4, it was fundamentally changed the perception of Mars, revealed the heavily cratered surface, and with the TV imaging camera, okay, first time the images of Mars were shown live, not live, basically after processing to the audience. People can watch the image and footage from Mars sitting on home. And it captured a total of 21 full images and one half frame. Okay, yeah, one of it showed by Dr. Alka Rani in her talk yesterday. So I'm not getting into it. But Mariner 6 and 7 did almost the same like Mariner 4, but increased the coverage. And we, by that time, the carbon dioxide rich atmosphere of Mars was known. Okay, from that. The main achievement of Mariner 7 and 6 both was to identification of the carbon dioxide rich atmosphere. Mariner 9, it gave us the first global coverage of Mars. Okay, so these slides, okay, it will be later when we captured on, and all the informations are all over there in the internet about the scientific payloads and the scientific discoveries. But what I want to show you this image. The first time ever we are seeing the surface of another planet in full, and it's still in the 1970s we are getting it. Okay, so Mariner 9. So after the success of Mariner 9, and as the global coverage gave us some glimpses of gully systems and some erosion features people have identified. So by that time, people were sanguine that Mars had watery past. So if the Mars has water, then the next question comes in mind that if there was life or there is life. To scientifically address these questions, we have sent the Viking 1 and 2 rover. Later on in this presentation, Netra will talk more about the life-related experiments on Viking 1 and 2. But I may focus on showing you these images. This image here, the black and white, the first ever image of Mars taken from close-up. Okay, taken by the Viking 1 lander. And this is first ever color image taken on Mars by the Viking 2. And when we think of Viking, most of us think of the Viking landers, but it has an orbiter module too. And that orbiter module gave us this kind of beautiful mosaics. Okay, there are strips and they have been converted into mosaics. Okay, now, so far so good. We were advancing our technologies and all this stuff, but to do science. Nowadays, if you have ever stumbled upon any paper of general geology on Mars, or you happens to be working on Mars, you must have seen this. So this is the Mola global topography. And let me tell you, this image, the whole of the topography, also shown by our previous speakers in this conference, it was created way back in 2001. Okay. And this mission, MGS, Mars Global Surveyor, it was sent way back in 1995. And the other important instrument, apart from the MOLA, was the TES. Okay. Professor Roop has used much of the data, I think. So the topographic knowledge so far, what we had before the high-rise or prism era was mostly coming from the TES. Next, the Mars Express, ESA had their own share here. And before CRISM, before the modern instrument utilizing the spectroscopic techniques, there was Omega. That gave us the first ever glimpse of the hydrous minerals. Okay. So our hydrous minerals and the sedimentary minerals and the altered secondary minerals, those first was identified by this Omega instrument. And HRS still relevant today. All the DEM, the DEM, the digital elevation model that people use to decipher the topography of Mars, are still been used the HRS are still been used. Okay, fine. So at this point, we knew that the Mars has some subsurface water ice and about the polar ice cap, and the atmospheric escape process was noted. And the global 3D mapping, I have already told from the achievement from the HRSC. Now, MRO changed everything. With high-rise, that can give you an image with a spatial resolution of 25 centimeters. Okay, that too is taken from the orbiter. It's a hell of a change in terms of technology. And the CRISM. So,
I will catch you later. Or not.
So, this CRISM, the CRISM data from running from 800 to 4,000 nanometers, covering the most of the visible, not the visible, leaving the visible, the most of the near infrared region, can give you extensive information about mineralogy of the Martian surface. And later on, people have worked like thousands of papers out of it. And there are very good catalogs are there with the CRISM analysis tools. You can just, if you want to use CRISM, you just have to click 2 or 3 buttons and you can get a map of an area with the hydrous sulfate minerals and the other carbonates at your display. Okay, fine. Apart from high-rise and CRISM, it has CTX and MarsC. Okay, CTS was also a context imager that can give you high resolution panchromatic images that can be also used for making the DEM, MARSI for the color imaging. But talking of color imaging, I may again share this slide. The global image of Mars that taken from the Mars orbiter mission using the MCC camera. And MCC onboard Mangalyaan, the Mars color camera, was till now the best possible resolution we can send to the Martian orbiters. Okay, and in terms of the color image. Okay, and it has some interesting instruments, the TIS and the methane sensor. The first time the methane sensor was being deployed to Mars. Okay. Okay, now I will ask Netra, George here.
So good morning, everybody. Right now, Shubham has given an overview of all the missions that have gone and what they have targeted. So currently, we can divide the science goal into 4 broad areas. The first being about life. So is there any extinct or extant life? What are the astrobiological signatures that we can look for, etc.? That is one facet of Martian exploration. The second one would be to characterize the climate of Mars. We all know that Mars has active atmospheric dynamics that happen. There are a lot of dust devils, dust storms, even the polar ice caps, which keep changing in size seasonally, which is still an interesting problem that we can target. The third aspect would be to characterize the complex geology of Mars. We know that it has some of the largest volcanoes. We know there is a northern hemisphere, southern hemisphere dichotomy that we see. There are a lot of aqueous alteration features that have been observed. So from a geological perspective, Mars is still a very interesting planet to study. And finally, when it comes to space exploration, what we are interested in is how much can humans contribute to it. So these are the broad science goals that we would like to tackle. And if you see the history of all the missions that have gone, you can sort of understand how the ideology has changed. So we started from directly looking for life. It then changed to follow the water. And it has once again come back to seeing what are the biosignatures that we can look for, which will give us the answers to the major question. So now would be a good point to look back and assess what the previous missions have done and how we can build upon it. So since we are in the broad context of this workshop, we're looking at a future lander rover-based missions. Let's spend a few quick minutes trying to understand each of the previous rover missions and what they have done. So starting off with the Viking lander. So this is a photograph of the lander along with its different payloads. And if you see at the bottom here, these are the major scientific experiments that they have done. So you had a biological experiment, which again, the results are highly debated even today. You had a gas chromatograph mass spectroscope. You had a meteorology package in order to actively measure the weather of Mars. You had radar for subsurface sampling. You had APXS, which is an X-ray fluorescence experiment to get the elemental composition of the soil. And you also had a seismometer. So since we've already discussed a lot of the results, I just put in one which we have not seen before, and this is from the gas chromatograph. And here you can see that these lines that you observe are basically contaminants. And what they do conclude is that there is no direct organic signature which they were able to get from this particular experiment, which again brings a big question mark to the search for life, so these organic compounds were the contaminants which they carried over there. So they are not from the Martian soil. So moving on, the ideology slightly changed that, okay, let's probably start looking for water. And if you see the Spirit and Opportunity rovers, the instruments can be categorized into the following broad categories. The first one are the cameras. So you have a panchromatic camera and you also have a microscopic imager on the robotic arm which can give you a close-up view. You had spectrometers which are supposed to tell you what the mineralogy is like. And you also had APXS which could go closer and give you what is the elemental composition. You also had this RAT, which is an abrasion tool to sort of expose the fresh surface. So these were the instruments that were present. And a few scientific highlights that they were able to give us was first these Martian blueberries, which is a very, very famous image. And these are the hematite formation, which again hints to a sort of warm and wet history in Mars. You had these gypsum veins, which are an evidence for water-rock interaction, which again allude to a wet climate in the previous history. You also had these outcrops which had iron, magnesium rich carbonates, which also say that there had to be a hot and wet period in the history of Mars. So now, if you want to build upon this, we start looking for the geochemical evidences, which is where you have the Curiosity rover, which had a drill which could collect the samples, and there was a very complicated sample handling mechanism. And the instrument that I'll be focusing on is Chemin, which is supposed to give the chemistry and mineralogy of the soil sample that you're studying. The technique that Chemin uses is XRD, which all of us know that it is a very common technique that we routinely use in the lab to get the mineralogy of bulk mineralogy of the samples that we want to study. So these are a full image of all the drilled cores that they have collected, and it gives you these beautiful rings that correspond to the diffraction peaks. And in most of the areas that they were studied, they could get the diffraction peaks of clay minerals, which again gives you a geochemical support for the existence of a wet and history in Mars. If we were to take that one step further, we have the Perseverance rover. And so building up off of Chemin, you had Pixel instrument, which is supposed to do microscopic XRF of the rock sample. So you're going in situ, you do a little bit of abrasion on the rock, you do X-ray fluorescence, it can give you these sort of mineral maps in situ. And there, they could see that there was some amount of phosphate which could be sensed. Now, this is not all that Perseverance can do, because it has a sample collection system. This is one of the most complicated mechanisms which has been developed in order to collect samples from Mars and then recover them in a future mission. So if you see here, there is a sample caching system inside the rover, and you have the drill that is mounted on a robotic arm. So this drill will go collect a particular core, which is then hermetically sealed inside this caching assembly, and then for future mission to retrieve them. So such a system obviously comes with its own set of challenges, and Shubham here will take over, giving an idea of what are the challenges there.
Yeah, thank you. So as they say, the path of success cannot come with full of roses. Like the first sample catching system, and the first sample, it was collected, the drill was ready, everything was there. But when they imaged the catched sample in under the belly, where the under the belly of the Perseverance rover, it seems empty. Okay. The first ever sample, you imagine, the first ever sample that has been collected on Mars was never recovered. So people gone crazy. And back then I was a PhD student mostly using the visible near infrared spectroscopic techniques. And for obvious reason, I was interested about Perseverance, but because it had its own IR and visible spectroscopic instrument along with Leaves and Raman. For the first time they were sending. So what we did, we just saw the first drill cone and the whole system. That's called the Rubian hole. They gave it name. So if you don't accustomed with it, every location that a rover goes, so first the science team, they give a location name to work on. Okay. So the first drill area was named the Rubian. And you see these points, these black dots, these are the Leaves target laser blast points. And we took IR data from these 2 points, one inside the drill hole and one outside the drill hole. This is covering the drill cone. Okay. So there we are getting signatures of smectite minerals like non-tronine, and without having any signature of water or hydration related features. So these are smectites, okay, but don't have water. So you see a smectite minerals that are clay without water, it's very loose, rheologically unstable material. And if you try to drill through it, it will obviously crumble down. See, that was the idea of not coming out of the sample, but don't worry. The first, the sample cache, the system, the sample is kept at the with the perseverance, stating that as a atmospheric sample of Mars. Okay, that is never wasted. Okay, later on, the LIBS, I'll just quickly show you what the LIBS instrument can do. So from 751 to 899 Sol, that is the Martian day of working time of perseverance, we can plot all the oxide data derived from the LIBS instrument. And if you see around here, in the y-axis, and x-axis is the just locations. Okay, so around this region, we can see some anomaly in the aluminium, iron, and Mg. So aluminium is increased exactly to those points where the iron and Mg is depleted. So geochemically, it is the most common way of alteration. But what caused them? It is, so now we look for the remote microimager photographs. It is also a camera just to look for context where the SuperCam instrument is getting the data from. So we see these three rock fragments, namely the skeleton glutes, rainbow curve, and the fringe lake. It was this white soapy rocks. Okay, so but you can see the discrete difference from the background of that area. So now again, coming back to our IR and LIBS data, that we can see those three data giving you the absorption features exactly matching with some interesting sodium-based zeolites. That is the natroalunite and the, natrolite and the analkyne. And now, what is the key takeaway from identification of natrolite? So it's a sodium zeolite. Okay. So then we first have to find the sodium source. And as the region of the where we are finding this is near to the Belva crater on the northern part of the Zozero crater, the bigger crater where the Perseverance has landed, and there is a northern delta we see. And then exactly in the middle, at the middle of the delta, there is a small crater called Belva. So now, due to this Belva impact, might have been a secondary induced hydrothermal activity or some volcanic activity. They may lead to a basalt, the fresh basalt that is coming out from the from the Martian mantle, or some regenerated crust to interact with the water-rich sediments, and that leads to formation of potassium zeolites. And this because the potassium can get the potassium can get through the system from the nepheline minerals of the basalt. And now there, this sodium source, we have to find for the sodium source. And the region of this Zozero crater is at the junction of the Martian dichotomy and near to the northern depletion. So if we've sure about the ocean hypothesis, the northern ocean hypothesis, maybe the oceanic water or the sodium that has been precipitated from the ancient ocean there, that can blown to that surface to increase the sodium anomaly here. But also it is not there, doesn't stop there, because this zeolite can act as a catalyst during the photodegradation of the nucleotide. So there are chances, so we may have found some biological activity in the future, because the identification of boron kicked a bit for that also. And here the sodium bearing zeolites, they can also point towards this some astrobiological implications. So having said that, I will pass on to Netra to briefly discuss the science gaps.
So we've had an overview of what are the science results that we've got till now. And these are the 5 key ambiguity areas that we were able to identify. The first one is the biosignatures themselves, because the question is still open as to which of those are biotic versus abiotic, and how would you really, sort of conclude this matter, for which we need to push the limits of resolution of the instrumentation techniques that we already have, which could be GCMS, Raman spectroscopy, or even laser desorption mass spectrometry. Our sampling till date has been limited mostly towards the surface, which we all know is anyway affected by the solar radiation. So the deeper that you can go, the more pristine matter that you can sample, for which we definitely need a deeper drilling core. Also, like how we listened to yesterday, collecting the sample even from the surface is a very key task. So probably we need to improve even our sample collection capacity, where you may have to break up these OPAL samples, for example, and then analyze them. There are also a lot of active processes that are happening on the surface, like dust storms, etc. So our weather monitoring would also need to improve. And as a whole, the water history is pretty uncertain. So doing mineralogy at a much better spatial and temporal scale can give us some idea about these aqueous alterations. And of course, nothing beats getting the sample back to the labs here and analyzing it with much higher precision. So we definitely need to, the question is still open, that we need to get back the samples. And if we were to do so, it's very important to choose these samples wisely, for which a lot of these in situ techniques together can give us which is a better sample to bring home. So that's it from us. Thank you.
Thank you.
Yeah, thank you, Shubham and Netra. Any quick questions? Maybe we can, in between, load the... Next is an online presentation.
Yeah.
Professor Zhang. Meanwhile, questions.
Wonderful talk, and thank you so much for giving the entire overview. And I think this is not just a question for the speakers, but generally in the audience. I have plenty of questions, and I can keep asking all those questions. But just from the ISRO point of view, I know that there have been a lot of reasons why we are going to the Mars. You already spoke about, okay, whether there is active life, which was the first Viking experiment, didn't work out, unfortunately, but it would have been great if it had. Then looking for water, and then looking for habitability. And I think in generally the global audience around Earth actually is moving towards whether we can inhabit
Exactly.
Mars, right? Of course, the moon is the first stop, but the Mars is the next stop. So just it's maybe more of a, not a scientific question, but
No,
what
to
is
answer
successful?
you in brief, the last objective of the 4 that I described is after the habitability perspective is over, then prepare for future human landing and habitability. So that is the first, final and foremost goal of Mars science as of now. That is sanctioned.
Globally.
Yeah, globally.
Following up on that, your chosen sites of landing will really depend upon what are your goals. Are you looking for biosignatures where there has been extensive work done already, or are you going to look for in situ resource utilization? Where is the future possibility of, looking at sites where you can make these structures? There are these global modeling where you know that there are less radiations. People in the space astronomy, they're already working on where is the least radiation in the whatever the regions of Mars, which would be exciting to actually build these structures you were talking about. So it's a different question altogether. And if we come together as a community, I would actually be excited about sample return missions from Perseverance, if that is something we are thinking.
Yeah, and it's a very broad topic that I think we need to further discuss. We have not. First of all, this is something that we have to do yet. So maybe.
Yeah, Shubham and Netra, nice presentation, very informative. So I have a query to Shubham. So you mentioned about the natrolite, and you considered that source of sodium as from that Noachian ancient ocean. So if that is the potential source, and you consider that a major ocean was there, so why the sodium abundance is very limited? Why we do not have much detection of sodium bearing phases, if that is the source?
That was another important question that we asked ourselves when we are doing this study. And to tell you frankly, haven't came up with a genuine answer. So we are still working on that too.
Yeah. So like, do we have like another mode of origin? Say like you mentioned it as like a low temperature hydrothermal alteration. Okay.
Yeah.
So
that
is
can be
there
possible.
any possibility of like a low temperature metamorphism can be considered?
Maybe because as it falls within the ejecta zone of the Belva crater, that can also be a cause. That if in the impact induced the hydrothermal vents, sometimes it happens. So then the groundwater can come through. That may have provided the sodium to the system. That is also a possibility.
Thank you.
There's
It was a map which is taken at a larger area, which the
Yes.
convergent thing. And then when you sample it to the compounds, whichever you distributed in different areas, this is very localized
Exactly.
enhancement.
The localized enhancement and those three data was collected from that those three chips only.
So the sodium thing is a overall purview, whereas for you to say the evolution to happen because of the presence of sodium, we will require more concentrated
Right.
observations.
Thank you.
there's
Thank you.
one
Maybe we take-
online question that we could try and address before we move to the next talk, and that is what historical data is available on the soil/ground properties to support the design and construction of future habitats, landing sites, or other infrastructure on Mars? So
I think later on we have presentations on this perspective only.
Okay, maybe we'll
Let's
get to
just
that.
wait
It's
for
not
the-
an easy answer, probably, but yeah.
sure.
So,
I think we'll move on to the
Yes.
next presentation, which is an online presentation. Dr. Zhang, you can get started in 10 seconds. Can you hear us?
Yes, can you hear me?
Yeah, in 10 seconds, I'll mute our mic and
Okay, good morning, everyone. Thanks for allowing me to present some of my work in robotics and AI here in this workshop. And as you can see from the presentation title, it's still in a very early stage, and we are exploring how robotics and AI can contribute to the gentle robotic manipulation of geological materials in planetary exploration. First, I would like to acknowledge the Ujanuga people as the traditional custodians of the land on which the Curtin Bentley campus is located, and would like to pay respects to elders past, present, and emerging. And before I start my introduction on the robotics and AI research I have been doing, I wanted to mention some of my track record, because all the research I'm going to introduce include all the works I have been doing in my current organization and also past organizations. So I have some experience as HKUIT and Australian Center for Robotic Vision, Alibaba, and QUT Center for Robotics, and now as Curtin. So you can see from the big picture, I have experience in robotics, AI, and also some indoor localization using visibilized communication. So first, I would like to focus more on the robotic manipulation thing. And this kind of research can start from my PhD, from the bottom right, the learning vision-based robotic manipulation. I hope you can see my mouse. The vision-based robotic manipulation is the major focus of my PhD research, and now I'm focusing more on the tactile-based robotic manipulation and extend the power jaw gripper to bionic hands to enable dexterous manipulation. So for those of you who might not know what is a power jaw gripper, is basically the gripper is shown in this part. It's just a two-finger gripper. We call it power jaw gripper. And for bionic hands, I think it's more intuitive to understand. And all the works have been done by my students, my supervisor, my mentors, and myself. And so I would like to acknowledge all the contribution and the collaboration from these people. So first, I would like to introduce the very early stage research from my part, which is learning vision-based robotic manipulation. In nowadays, you might already be aware of a lot of humanoid robots research, and we call it embodied intelligence or embodied robotics. So back in 2015, which is still the early stage of exploring neural networks for computer vision tasks, and also some of the planning tasks was DeepMind did for the chess. And at that stage, my research was to explore how these kind of artificial neural networks can be applied for robotic tasks. And this is the last work I did during my PhD. Basically, it learns a policy using neural networks to map raw pixel image inputs to model commands. So basically, the inputs to a neural network are images from a webcam, and the output of the neural network is the how fast each model should move. Because that's what you can see from these humanoid robots. Not really humanoid; it's just dual arm robotic systems with no legs. And we have 7 degrees of freedom of each arm. And so we have to, for a neural network, it has to output 7 velocities to control each joints, how fast it should move. And as you know, for a system which use webcam as the perception part, the images are very cheap. We can just record all the output from a webcam as the inputs to the neural network. But to train a neural network to do the task, we also need the labels for the output, how much velocity should be allocated for each motor. And labeling providing those kind of labels can be costly. So we think probably we can make use of, say, the all-the-ground truth in simulation to help us provide very low-cost labels to reduce this kind of provide the costly process of providing labels for real-world images. And then we developed this or proposed this kind of adversarial discriminative scene-to-real transfer policies, which can transfer the model trained mostly using simulated data to real-world scenarios. And what we did in this work is basically proposing a mechanism which can tune a bit the distribution of the output for simulated data to be as similar as to the output for real-world data. And in this kind of tuning process, we don't need real-world labels. We just need a large amount of real-world images and also synthetic images. So through this kind of approach, we can achieve a decent performance as what you can see from this video, and also some unseen situations. I think it's already repeating. We can go to the last part. Actually, my hands were not seen in the training process. So, but you can still observe a decent performance of the robotic arm to control its end effector to reach the target objects. So in this task, the blue cuboid is the constant constant target. So you can see no matter how I move the desired targets, the model can always control the end effector to reach the targets, even though some unseen objects like my hands appeared in the in the image, which were not seen in the training process. So this kind of performance demonstrated the robustness and generalization of the model trained through these kind of adversarial discriminative scene-to-real transfer approaches. Okay, that's a very early stage work compared to the recent works nowadays, which we call its vision language action. So at that point of time, we just use a relatively small scale of neural networks to implement this task. just wanted to give you a big picture how machine learning can be used to enable some kind of like robotic tasks. And a more recent work, which was done by my PhD students, is to like enable learning fabric manipulation in the real world with a small amount of human videos. So like what I mentioned in the previous work, we tried to make use of synthetic data to reduce the requirement of large amount of real data. And in this work, we formulated the problem from the high level, and the inputs to neural network is still an image, but the output would be like somehow to decide where the like picking points should be and where the destination points should be. And the low-level control, I mean, the control commander to control how the arm should move, it was implemented by conventional controllers. We don't need the neural network to implement such a like end-to-end policy. And in this manner, we were able to achieve the performance you can see in the video by using, I think it's just 15 human demonstrations, if I remember correctly, but you can check more details from this paper and also this project page. So those two works were purely vision-based like approaches for robotic manipulation. And as you might be aware of the role of our human skins, how we make use of our human skin to enable our dexterous manipulation in our daily life. So basically, they play a very critical role, and pure vision somehow has its own limitation for dexterous manipulation. I ever had some experience with teleoperation for two UR4, not UR5, probably UR10 robotic arm with two shadow hands. And at that point of time, I can only observe how this kind of dexterous manipulation performs through my eyes. And I find how difficult it could be to do those type of operation without any force feedback from the force enabled gloves or those sort of things. So we do think tactile or haptic or say skin style sensing modality are critical to enable robots to do more dexterous manipulation tasks. And to achieve that goal, one work we did was to design the first object, design the instrumented objects to enable the first objects, measurements of how gentle a robotic grasping could be. So like what I mentioned, the fragile objects are sensitive to grasping force. If we apply too strong force to grasping objects, ideally, if we can apply indefinite force, we can grasp anything. But the side effects could be damaging the objects itself. So, and some solutions have been proposed to solve these kind of problems, but ways of directly measuring the force applied on the objects is still under studied. And then nowadays we can see a lot of soft tactile sensors, which can sense the contact through the sensor itself. And we were thinking about, can we use these kind of soft tactile sensors as instrumented objects to provide this kind of first object's view of how strong the contact is from a robotic gripper. And from this idea, we developed a quick proof of concept by designing instrumented objects, use Hall effect sensors, and the Hall effect sensors are embedded into the core, internal core, and we have a outer shell which includes a decent number of magnets to provide the magnetic field. And then we can observe the Hall effect sensors signal changes while the objects is being grasped by a robotic gripper. Like what we can see over here, the signals can change in a way like this, and we can leverage the machine learning models to estimate where the contact is and how strong the contact is. That's a proof of concept design, and definitely we can explore like better designs to achieve this kind of goal. And to enable the functionality of the neural network, we need to collect some data, and we use the CNC machine. I call it CNC machine. Actually, it's a 3D printer, and we integrate the force sensor on the printing part, and we can use this kind of facility to collect the data with labels, the contact location and the contact strength to train the neural network. And this would be the force like distributions of the data we collected. Okay, you can see, like say, the strength is much stronger in the central part of the objects. That's because we use a constant like displacement to collect the data. And due to the stiffness of the different part of the objects, then we achieve this kind of distribution of force ranges. Yeah, this is a proof of concept work we did to like for enabling first objects measurements on the context from robotic grippers. Hope this is interesting for you. And you can see this. Basically, the left side is the predicted heat map, and the lighting part is the contact location, and the color indicates the strength of the contact, and right part is the grand choose. And you can see, like in most cases, the neural network can estimate the contacts in a like accurate way. But we also observed some limitations of the current design, and there are a lot of things to explore to have more mature like designs to enable reliable and stable measurements for these kind of purposes. We also like to enable this kind of gentle manipulation, and we need to know like what would be the minimum force to grasp an object. If the force is, like say, is too little, there is a possibility to drop the objects, and that's also like a disaster for this type of a grasping task. So I call this kind of thing as non-slip minimum force. And to achieve that goal, we also collected some data sets for incipient slip detection, and also comparing how different type of sensors could contribute to this kind of like detection. So I call it incipient sleep detection because we care more about when the sleep is going to happen. So if we can use this kind of signal to help adjust the force, like how much force we need to apply to grasp like a fragile or brittle objects, then this could be a like good strategy to enable non-slip minimum force grasping, which is the gentle situation, the most gentle situation we can achieve. And the data set compels 4 types of fingertip tactile sensors. One is called U-Skin, which is an off-the-shelf sensor from a Japanese company. And another one is a vision-based tactile sensor, which is called Gel Size Mini. And another one from our collaborator in Singapore is called GTAC sensors. Basically, we compile different types of tactile sensors to see how different sensing mechanisms can help achieve the goal. And we collected the data to cover 39 objects because we extended the coverage from 14 objects to 39 objects. And like what I mentioned for the vision-based robotic manipulation, actually the labeling process is really costly. And to reduce the cost, we developed an auto-labeling tool for finding when the sleep is going to happen. We use also a computer vision-based machine learning model to track the motion of the objects, and you can see from this video. And we use the vertical velocity to estimate when the sleep is going to happen. And I think you can observe like roughly somewhere, yeah, here, you can see the sleep, the label here. You can see. Yeah, there are some tiny motions which can be estimated from the tracking results. We also did some like re-evaluation at existing fingertip tactile sensing data sets for inferring objects objectives. And we through this kind of re-evaluation, we got some key observations summarized here. And if you are interested, you can probably read this paper to know more about the details from a high level. Basically, one tactile sensor is sufficient for symmetric use cases because there are a lot of redundant sensing signals for symmetric objects if we just use jaw gripper to interact with the objects, and vibration, temperature, and also spatial downsampling or temporary downsampling, how they will affect the performance for inferring objects objectives. So from a high level, the data set itself used two fingertip sensors assembled on a power jaw gripper to interact with different types of objects, and the data set uses those tactile signals for inferring objects objectives. Okay, I won't go too much into detail in this part. And apart from those, say tactile-based works we did, we also had some early stage exploration of dexterous manipulation with bionic hands. On the left side, the video shows the vision-based teleoperation of an off-the-shelf bionic hand. And you can see this visualization is actually contact force from the fingertip sensors on the fingers. And this part, one of my students explored how this kind of tactile signals can be used to enable non-slippery minimum force grasping of sticky notes. And the right side, the videos show the duplication of an open source bionic hands. And these are some other works we did for machine learning based robotic manipulation. Yep. And also the design of a bionic hand with four sensors covering the whole hand, because what we discussed before are more about fingertip sensors. But actually in our daily dexterous manipulation of different household objects, the contact sensing covering the whole hand contributed a lot. So all those works are the works related to tactile-based gentle robotic manipulation, and we are now at the stage of exploring how these type of techniques can contribute to the manipulation of fragile, biological materials. And we this work is still in a relatively early stage, and Martin told me a lot about the current situation of hot spring silica sinters, and which I think preserves biosignatures and also a lot of contextual informations which can be used to study the history and the history of different rocks, either on Earth or on Mars. And those materials are very fragile and brittle. And so we think probably some tactile-based gentle robotic manipulation can contribute a bit here. And that's our idea. And we are exploring this kind of idea in a very early stage. And apart from the robotic manipulation works, I also did some works in general, pure AI thing, machine learning for representation learning, and also optical neural networks, and some kind of how we can make use of remote sensing or drone drone visions to help monitor the traffic condition. And we also had some work in collaboration with MIT and SINTEF from Norway for salmon fish cutting, which uses also tactile-based robotic manipulation to achieve gentle manipulation of expensive food materials. Again, that's pretty much what I have been doing, and I'm looking forward to seeing how gentle robotic manipulation can contribute to fragile and brittle geological sampling. And happy to take any questions.
Excellent presentation. Thank you. That was very interesting. I had a question on the examples that you were showing. All of the gentle manipulation that you were demonstrating, the objects were loose on the ground. How do you make that next step and start thinking about how much force is actually required to remove that material from the ground while still maintaining that gentle grip?
Yeah, that's a good question. So basically, if we have a closed loop control, which can sense when the slip is going to happen, the force can be adjusted accordingly. Yeah, and another option could be if we can have some prior knowledge to help have a good predefined strategy, and we can combine this kind of prior knowledge to with the closed loop control, which can make the solution much more reliable. So that's our thinking on this regard.
This is Steve Ruff. I'm curious about how the robotic arm is sensing the depth dimension. Is it like a stereo vision system? How do you get that third dimension sensing?
So for the depth sensing, apart from the special situation in space exploration, we have stereo vision, like what you mentioned. We also have some other type of RGBD sensors or even lasers, but that's just for usual use in our lab environments. It's regardless of the special conditions in the space exploration, and we would like to explore more suitable solutions for that purposes, particularly for space exploration.
Thank you.
Yeah. Any other questions here? Just a quick question. Dr. Zhang, you had the thumb at the middle, and I was just wondering, is there because the usual thumb position is different. Is there a particular reason? Do you find that easier for certain kind of objects? Is that why it's designed so?
Sorry, you mean the objects being grasped in the experiments, or?
I think the previous one where there was an animation showing the thumb movement, where the thumb was placed sort of at the center rather than at the edge of the hand.
This one?
Yes.
Yes, we think probably this kind of design can help achieve similar degrees of freedom like human hands, but with only 4 hands. That's the motivation, and the students is still in the process of assembling everything into real world bionic hand for further evaluation. Probably through multiple iterations, we will have a different design, but this is the initial idea.
Thank you. Thank you very much.
No worries. Yeah.
Thank you, Dr. Zhang. I think we'll have to move on to the next presentation. So if you could kindly unshare your slides, and thank you again.
Yeah, thank you.
So our next presentation is by Professor Alok Kumar, who is a faculty member here in the Mechanical Engineering Department. So over to you, Alok.
So how long do I get? 20 minutes. Yeah. Yeah, I know. I'm standing between. I'm standing between you guys and coffee. I know it's a really bad position to be in. Okay, so I think there's far more experts on Mars here than I've ever met in one room. But I'll talk about something else. My basic topic or area of interest is ISRU, which is obviously short for In Situ Resource Utilization. When I started on this particular topic, I tried to figure out where I should draw inspiration from. And I think obviously the biggest source of inspiration should be our own planet. So we know that biomineralization, this is a fossil that was gifted to me. I mean, you guys are probably you probably have far more experience with fossils than any other engineering department. In most engineering department, this is a novelty by itself. But this is an ammonite, and you can see these are the scales of calcium that have been left behind, and that's why you can see this, the fossil is preserved. And this process of biomineralization is actually a very, very extensive process that happens in organisms of all sorts, can create endoskeletons, exoskeletons, and everything. Biamineralization also occurs in other locations, for example, which are not fully well understood. For example, this is a termite hill. I took this photo in Gir. There's quite a few termite hills on the campus, by the way. So if you have not seen them, you can see them. This is a beautiful paper on how this biocementation happens for termite hills. This is actually a paper from ISC, the ecology department. They did a fantastic work on how the termite actually uses its saliva, and there's bacteria and etc. out there, and they put it together, and it's a very beautiful porous structure, which also has a lot of strength, right? So the bottom line being that biocementation is a very interesting process. I've shown you two examples here. This is as an ammonite and one as a termite. Obviously, endoskeletons, exoskeletons also come under that category. I look towards much smaller organism. The bacteria, there are a lot of microbes that are very well capable of biocementation. Why so? It's still not a fully solved question, but we do know that there are certain microbes. For example, there's some microbes in the soil. This is a photo from my lab. This is a bacteria called Sporosarsina pasteurii. It's a gram-positive bacteria isolated from the soil. Loves high pH environments, and given the right conditions, what it can do is it can create, so it's actually an enzymatic process. The bacteria secretes a certain enzyme, which leads to, actually there are many processes, but if there's urea, this particular bacteria uses a process called ureolysis. So it produces an enzyme which leads to the hydrolysis of urea and creates carbonate ions in the solution. And if there's calcium there, what you will end up getting is a calcium carbonate crystal like this. So this is an SEM image. You can see these bacteria here. There's a little bit of EPS, or the extrapolymeric substances that are also being secreted. As I said, this is from Sporosarsina pasteurii. This particular process is known as ureolysis because this bacteria loves to hydrolyze urea. Evolutionarily, the answer is because this bacteria evolved when the first animals started walking on this planet. So there are a lot of animals, they're peeing in the soil. The urine has a lot of urea. Somebody needs to utilize that. In the ureolysis process, there's nitrogen that is now left in the soil. So there are other organisms which can use the nitrogen. So there's ammonium in the soil. So there are other processes as well. This is not the only one. This is very well studied in some sense because there's a lot of environmental microbiology people. But more than environmental microbiology people, it's been civil engineers who have been using this actually. There are other processes using, for example, photosynthesis. There's also bacteria that are that can work in fully carbon dioxide condition. Oxygen deprived conditions. So there are methanogens which can use other cycles, chemical cycles for similar process. Anyway, end product of one of these biocementation processes, the bacterial biocementation process, is always some kind of a calcium carbonate. So it's usually, it could also be magnesium if there were magnesium in the environment, but usually calcium carbonate. And one of the things that happens for this particular microbe is that it locally changes the pH. So the pH keeps rising, goes over 7, goes over sometimes 9, etc. in that condition. The thing that we got interested in is what it does to the soil. So I'll just show you 3 SEM images. These are going to get zoomed in more and more. So you can see some things, right? Some small granules here. Let's see what it actually is. So this is a zoom up of this. You can see these globules. You can see this bacterial mat. And this is a far more zoomed in image, right? So this inside this particular thing, this is calcium carbonate. This is the bacteria. And you have all the microbes are actually connected to the EPS mat that you can't see. The EPS is not very heavy, the extrapolymeric substances, but it is enough to cover that. So when you leave this bacteria in the soil with the right conditions, what it can do is it leads to soil hardening. So the soil hardens. It has been proposed that this bacteria, this is the way of leading to healthy soil ecology. So what it does is it preserves the soil against erosion, but at the same time, it releases ammonia, which the plants, etc., can use. So it creates a symbiotic relationship with the other organisms around it. But if you were an engineer and you were to put this bacteria with soil, the regular soil that you get, you will end up getting a very hard structure after some time, especially if you have no other biological activity. If you take everything out, it leads to a hard object, almost like a brick. What the bacteria secretes remains an open question, exactly what type of polymer, etc. But we'll not go into that. So, okay, now since we are talking about extraterrestrial life and all that, I thought, okay, since it works so nicely with soil, it makes a brick. I mean, we could take the lunar soil simulants and we could make a brick out of that. ISRO has developed, at URSC, they had developed lunar soil simulant. This is a photograph from the mines in Salem. So there's a huge anorthosite deposit in Tamil Nadu, and there's a group that were able to figure it out, and they have created this, they've mined this rocks and they've pulverized it, created a lunar soil simulant of ISRO itself. So we have a local variant. I was able to get it. We had a project with URSC. And then I said, okay, I mean, this is something that you don't really need to get into, but as you know, it has a lot of silicon dioxide, aluminum oxide, calcium oxide, and others. What it doesn't have is clay, right? I want to point it out because, you know, microbes love clay. They're not going to, otherwise we would have the Thar desert would be thriving with microbes. That doesn't happen, whereas microbes need water, and water is retained by clay in soil. So clay is an important constituent, which lunar soil did not have. That is that when I started, I was sort of ignorant about that. So I just took lunar soil, mixed the bacteria, and I thought, okay, you know, it will probably work. The process that we developed is a very simple process. It is just like the way you construct your houses. You would have seen concrete being mixed into a slurry-like structure, into a slurry, and the slurry is poured into different, you know, molds, right? So what we did is we would mix the bacteria with this lunar soil simulant, and then we have a slurry, and the slurry can be poured into any shape you want. So whatever mold you create, cylindrical, cubical, etc., you can just pour it into that, and then we press it a little bit to consolidate it, and then leave it out in the lab for 5 days. No fridge, nothing, you just leave it out. You can leave it even outside. You don't want the water to evaporate from the slurry too much, but you can just leave it out. Initially, it took us 5 days. We later on made the process better. We now can do this in 3 days. Okay, so my expectation was, since this bacteria, when present in soil, if you just take clay and put this bacteria together, it makes this really hard brick-like structure. That is the same thing that will happen with lunar soil, but it didn't. The bacteria died, and whenever I take the mold out, everything would crumble into its constituents. The reason is there was no clay in the lunar soil simulant, or even in the lunar soil, there is no clay. And if I forgot one of the first two lectures, they had shown these SEM images of what the lunar soil looks like, or the Martian soil looks like. They're very jaggedy, etc. structures. That's not an ideal environment for bacteria. So they were dead right away. So I would not get any good results. I'll just show you what I started with. Yeah. So when I did some compressive strength, this LSS is lunar soil simulant. SP is the bacteria, Sporosarsina pasteurii. It would just crumble in my hands the moment I took it out. So no real compressive strength by itself. So I realized that we had to make the environment more livable for the bacteria. Obviously, I cannot put clay in there. Then you have to transport clay from Earth. That doesn't make any sense, and clay is a very valuable resource. I instead looked towards other alternatives. one alternative for me that struck me was biopolymers. And India actually produces a lot of biopolymers, a lot of fruits actually, one of them being guar. I don't know if you have seen it. It's a small green fruit, grows a lot in northern India, Rajasthan, Haryana, that belt. If you take that fruit, you dry it, pulverize it, it becomes a powder. And it actually, if you mix it with water, it becomes a shear thinning fluid. And it's a biopolymer. And it is very cheap, very, very cheap. So I purchased that because you can purchase like a kg for 100 rupees or something. And I mixed that with the lunar soil simulant. I recreated the slurry. And this time I got not bad. I mean, this GG stands for guar gum, which is, I was adding in about 1%. So if you have to make 100 kg of this brick, you'd have to have like a 1 kg of guar gum. Yeah, I'll come to that. Yeah. So we are getting something around 2.5 to 3 megapascals. Ice cube at around 0 degrees has a compressive strength about 5 to 6 megapascal. And with ice cube, you can make an igloo. Civil engineering requirement, I am told, for brick compressive strength is greater than 3. So there are houses in Bangalore which are made using very traditional techniques of just using mud, etc. Their bricks are not as hard as the kiln burn bricks. So they are about 4 or 5 megapascals. Kiln burn, the ones you use to construct this kind of house, this will be about 10, 15, 20 even. Right. So, but on the lower threshold, 4 or 5 is enough for Earth. And obviously, if you are looking on Moon, where 1/6 gravity, this is not too bad, right? So we were able to get some good results. And what we realized is that there's a lot of interesting biophysics that is going on inside it, because when we did GCMS profiling, we saw that this guar gum was being utilized by the bacteria. One of the other things that we saw when you take SEM images is the lunar soil gets coated with this biopolymer and most likely makes it more habitable for the bacteria to live, right? So you're creating a better environment for the microbe to live. And we don't fully understand what really happens, but if you do this right, we were able, so this is, by the way, this is one of the bricks that we had made. When you take it out, it's all fluffy, etc. On the outside, it's not very dimensionally consistent. So as an engineer, we love dimensionally consistent things, right? So we put it on a lathe and it is strong enough, even at 3 megapascals to, this is a lathe filter, and you can, so you can make this really dimensionally consistent structures now. So that was the good news. We published this, I think the first results came out in 2020. Post that, I mean, my first interest became, okay, now that we have done lunar to a certain degree of success, let's move on to the Martian one. And one of the big, I mean, I don't have to preach to the choir here, but the big difference so this is your EDS from lunar soil simulants, and this is your EDS from Martian soil simulants, and what you have is a lot of iron, right? I don't have to explain to you guys. You can tell me why it's there. But it makes a lot of difference to the microbe. And that was something that we did not anticipate at all. I mean, we had such a good success. We had the lunar soil, we mixed it with our bacterial material, and you had this really, really nice bricks that I could even put on the lathe. How difficult is it? And what happened was, again, when I did the same thing, this would just fail, and all bacteria were again dying. That was a surprise to me. We spent about a year failing, and we actually we figured out the right answer to that. But before that, interestingly, what happened is somebody wrote a long review article on Mars colonization, and there's a lot of authors here, and they had a full paragraph on our work. And they had said that what we had done with the lunar soil, I'll just save you the trouble of reading the whole thing, will not be possible with the Martian environment, because the Martian environment contains a lot more stressors for the bacteria. So it's a much more complex environment. It has perchlorate, it has iron, it has a lot more stressors. So it is not going to be, the same process is not going to work, which we were figuring out. As the paper had come out, we saw, yes, it is true. It turns out that, so remember I had said that this bacteria drives the entire process through an enzyme. So it creates an enzyme called urease, and the urease breaks down the urea. So urea is CONH2, and the urease breaks it down. So the bacteria, to be able to successfully do its job, has to be able to create this enzyme. So if you look at the structure, and this is the big molecular structure. The interesting thing is right here, these two green blobs, those are nickel atoms. So there are two nickel atoms at the center of this urease molecule. And what we realized is that most likely the presence of iron was hindering, the bacteria is probably mistaking the iron with nickel, and it's not able to, produce urease. So that, okay, maybe one quick solution would be to add a little bit of nickel salt to it to help the bacteria, not get confused with the iron, and so artificially give some nickel. So we did that, and it fantastically worked. So for example, this MSS is Martian soil simulant. This is your MGS1 simulant from, I think Exolith Lab. Now it has become another space tech resources, right? So MSS, this is the bacteria. When we added the guar gum, without the guar gum, it doesn't even form a brick. With the guar gum, we were able to get to about 1 megapascal, which is not good, not bad. I mean, it's bad actually. With a little bit of nickel, we were able to get about 2.5 megapascals. But with the guar gum and nickel, we were able to get up to 3. So we were able to repeat what we had done with the lunar soil now with this addition of nickel salt. And then we realized, we had never added nickel in the lunar case. Maybe if we go back and do that, it will help our situation. And that's exactly what happened. So when we redid our old experiment, and this time we added a little bit of nickel, we got compressive strengths up to 5 to 6 megapascals. So not bad at all. Now we have reached to where ice is, right? So we can definitely make igloos out of that. Okay, so we wanted to keep on increasing the complexity. I'm not going to go into the whole thing that we have been doing because we have been working on this for 8 years now. So I can go on for a whole hour about all the different experiments we had done. When Shubhanshu Shukla started working with us, he's the Indian astronaut who recently went on the International Space Station. He was very fascinated with Mars, and he wanted to, work on this type of project. So we figured that one of the key other stressors that we had not worked with was perchlorate. So this detection of perchlorate has been consistent, about 0.5 to 1% perchlorate is estimated to be the Martian sands and the Martian regolith. And this is usually calcium or magnesium regolith. Calcium or magnesium perchlorate. Right? And perchlorate is, again, poisonous to bacteria. These are soil bacteria. They've grown up in earth and they don't like things like that, right? So when we did experiments with, this is another strain, Sporus arseniopasture, when we did this experiment in the lab, this was the healthy case where we did not put any perchlorate. And as we kept on increasing the perchlorate, we saw that the bacteria starts clustering together. It also produces a lot more EPS or extracellular polymeric substances, which is a usual sign of stress. So the bacteria is feeling a lot of stress from the perchlorate. So by the way, MGS1 comes with no perchlorate, right? Actually, all of the Exolith Lab samples come with 0 perchlorate. Obviously, perchlorate is a explosive. You don't want to ship it. So we had to modify the MGS1 with extra perchlorate. And when we grew them, no surprise, with perchlorate, all the bacteria die. So what was happening is and most likely, while they are still living. This is, by the way, this is with no, this is just with perchlorate in an aqueous solution. You can see this, but when you put it in a brick of the Martian soil, almost all the bacteria die in about a few days. So if you are taking the brick out after 5 days, it basically again crumbles in your hand. These are some interesting SEM images. We added a little bit of guar gum again to make it more habitable. Then we were able to see bacteria. So when you add a little bit of guar gum back into the into this modified Martian simulant, what you have is you can start seeing a little bit of bacteria, but you also see these micro bridges of the polymeric substances. And when you add a little bit more of guar gum, you can start to see a lot more bacteria in the state. So it is a very strong function. The guar or the biopolymer is somehow making life more habitable for the bacteria again and again and again. So, I mean, we have found the key to the success is some biopolymer to make life better for the microbe. And we repeated the same experiment. These are all the different results with this Martian simulant, now modified with perchlorate. I'll just tell you the last couple of results. So if you have this bacteria plus guar plus the nickel source plus perchlorate, you can, once you have the guar gum, you can get up to again 6 megapascals. But without the guar, just the bacteria and the perchlorate, you get nothing. The bacteria die. With a little bit of nickel, you can make life better. But these are all different controls, if you want to say so. But the guar is absolutely essential. In the interest of time, so most of all these experiments, as you can imagine, are being done in Earth conditions, right? So we are adding the complexity one by one. We added perchlorates. We realized that the iron is a toxic mineral. We have now isolated in my lab bacteria that will survive in a pure CO2 environment that are capable of MICT. We haven't gotten any funding yet for that, so we're not being able to proceed with all the different experiments, but those microbes have been isolated, and we have done that. We did get a little bit of funding for looking at the effect of biopolymers. Again, not going to the full aspect of it, because one of the key things about biopolymers is, or these bricks have a substantial amount of porosity. So if you do something like a porosimetry test, or you do a CT scan, what you'll find is the porosities are all the way up to like 30–40%. So we have modified our processes. This is a diagram that solid mechanics people use a lot to characterize different materials. As you can see, this is on this side is the strength. These are two independent parameters, strength and density of materials. You have foams, you have natural materials here, you have polymers here. These are ceramics, and then you have metals. Initially, when we had made our space bricks using just the bacteria and our modifications, you were landing up somewhere here, which is somewhere in the area of polymers. Now we have modified our process altogether, and what we have started doing is just adding biopolymers and compressing them. So we have a huge 20-ton compressor in the lab, and we before we process the slurry, we take it through the compressing machine, and we compress the entire thing so that porosity is lesser. So now what we have found is post a compaction process, your porosity is dropped to like 10%. Once they drop to 10%, its strength actually increases significantly. So now you can easily get 15 megapascal strength. And this thing we have also made a low pressure chamber where we simulate a Martian level pressure, and we have been able to cure the entire brick there. Although then we do a post-sintering process, which is again in a natural lab. But we can reach here easily. So the interesting thing though, this is now it's more or less become a inorganic process. Even though you are sourcing biopolymers, the rest of the processing is without bacteria. But with bacteria also, I mean, we were able to reach here, which is extremely, it's not bad at all. You have reached the domain of polymers, and for gravity of Mars or Moon, that's not bad for a construction material. If you add a little bit more to that, some, in our buildings, we always add some extra. For example, you have iron rods running through our cement structures, and that provides extra reinforcement. So if you add reinforcements, you can easily still work with these. So these biobricks that we made, we were one of the first labs in the world to have reported using bacteria to make these bricks from Martian and lunar simulants. This process of increasing the strength is key, but there are still a lot of open questions. We still don't know exactly how the guar gum really helps the biology of the process. So there's a lot of interesting biophysics questions that are still out there. bacteria find the lunar and Martian regolith an inhospitable environment for us. I mean, I know there's a lot of talk about panspermia. There's also a talk of reverse panspermia, where microbes from here, when they land on other planets, are going to start living there. But it's not going to be an easy process unless you make it easy. The life has grown, adapted to this environment, and critical things are missing. In fact, this entire journey made me appreciate Earth a lot more. I'm not a geologist by any big stretch of imagination, but I learned a lot of things about these minerals and clay and how they are an important part of our lives. So thank you. I'll cut. This came out in the local news, so this was an interesting highlight after we published our paper. And these are all funding agencies. So thank you.
Wonderful talk. Thank you so much. Really exciting. Will you be trying to add a little bit of clay to get increased strength? As you said, that's a really key component.
It is, but see, the whole point of ISRO would be you'd have to take some material from here. The moment we add whatever binder we add on Earth, you will have to be basically transporting it. So clay, to me, I mean, I don't know how practical it is because it's an important resource on Earth as well. Whereas something like biopolymer, you can grow. So that's not an, it's not an inexhaustible supply. You can just grow. It's not conserved. Whereas clay is conserved in some ways.
But there is clay discoveries of clay on Mars. Kaolinite. Yeah.
So so we have worked with some of those clay samples. The bacteria survive much better there. So if we source our material from those locations on Mars where there's extra clay, that automatically will take care of some of this problem.
And just a point about the guar gum. I mean, it sounds like that's probably just a food source for the bacteria. It's providing carbon for them to grow and multiply, right? If you have nothing, if you have
no.
carbon.
Okay. One thing I did not mention is we were providing a carbon source. So there's glucose being provided to the bacteria in all the experiments. So the guar gum is doing something extra.
Yeah. So excellent presentation.
Thanks.
I loved it. So much earth science.
Yeah. I should move to this department.
But you have more. So you have more challenge for Mars. I must tell you that the environment is not same as that of Earth. It is saturated with CO2. CO2 is strong corrosive if you think of as a cement when you expose it to 95%. If you have a wet condition, it will have a strong effect in terms of your durability of your material. So I don't know how good it will be, but I think this is the right direction. If you can convert this to silica, which spoke yesterday and others, it can be a wonderful cement if you introduce bacteria to precipitate silica, the same way as you're doing it carbon.
So I don't know of bacteria which can do it, but there are some diatoms which make silicates. So we'll have to look into that.
So shout out to you as I agree with the last bullet point. I also appreciated the Earth after I moved from physics to, biophysics to geomicrobiology. So all the people who are working in geology department, huge respect. So the question I wanted to ask you is actually following up on what Shama said, is that any kind of metal in concrete structure, which eventually you're probably hoping to build in lunar or even Martian environment, would raise some secondary radiations, right? So is there something known that what is the minimum iron or any kind of metal concentration which will be okay, or, because it's all depends upon the concentration of those metals in the space bricks or environment?
I don't know the answer to that because we only worked with the simulant that we got. But by the way, iron is not toxic to all organisms. Like this particular organism most likely confuses the nickel and the iron, and that's its metabolic process gets affected. There are microbes which love iron. So you have, I forgot the name, there are a lot of bacteria which can actually transport electrons to metals, and they would thrive in this environment.
I was actually going to ask you, like, are there other strains of bacteria that may be useful? Maybe that's something that you can suggest.
Chuanella. Oh, okay.
For all these bio bricks is to eventually build these structures, right?
Yeah.
And the structures, while they need to be strong to be able to build these structures, would also need some radiation resistance, right? You need to
radiation resistance.
protect your
If I understand, after the job is done, the bacteria are not needed, right?
Yeah. They're dead after the process is
Oh,
over.
no. So I'm still talking about you amended it with iron and nickel to make those bricks.
Right.
The iron and nickel will still survive on those. The bacteria is dead, but the iron and nickel is still part of that space brick.
Yeah.
Yes.
So I just wanted to know whether there will be any secondary radiations which would be emitted. This is a question I think
That
was
would
asked
be,
earlier. But do we know how
to the
much iron can be added to these structures?
But to the, okay. Oh, you mean how safe that structure would be?
Correct.
Okay.
Do we?
Okay.
I'm talking
Understand.
backward.
Yeah. Would depend on how much you add, probably. Like,
Yes, that do we?
I guess you will need to calculate. But I
Make a
hope
quick
very
announcement
metal-
before a few more questions. There's coffee being
That's
served
great.
outside. We'd love to, have some of you can start because we are
Yes,
running 15
yeah.
minutes late so that we can start Ritu's talk by 11:30. But let the questions continue. At least some of you can go for coffee.
Yeah. But Alok, I also wanted to ask, like, would there be, like, would this all be done? Yeah, please disperse and go ahead for the coffee. I was thinking of like contamination or planetary protection aspects of Mars. So would this be done in a very environment where the things won't go out? You make the brick and then you throw the brick out or something like that?
I don't know. I mean, people talk about it all the time, but I think it's partially a sham. But by the time we are landing there, we have left our poop, our urine, etc. on Moon, right?
But there, I guess the UV radiation.
Sure. That's true. But I mean, these bacteria are going to die anyway. But once you step onto another planet, you are going to take everything with you. I mean, we are 80%. I mean, that research is still debated, but most of our cells are bacteria.
Yeah.
So you are shedding it everywhere. It's once you have landed there, it's just going to be there. So
Or I guess you make something where you make it inside and only throw out the brick. I mean, without.
This is the elephant in the room about all of this. I'm surprised you didn't. I figured you would be like in. Yeah, so you're right about once humans arrive, the potential for contamination goes way up. But what you're proposing is just going to enhance that contamination by many-fold. I mean, you're going to have, you're going to have dead bugs in your bricks, but now those bricks are essentially, there's an organic contamination source that will ultimately make it worse. So I understand the sort of philosophy that once humans are there, we've already accepted some level of contamination, but just I think you at least need, in a talk like this, you should at least address the elephant.
So I belong to a very different school. I don't believe, so unless there is life already there, unless we, see, humans on Earth thrive in our local environment. We know that we live symbiotically with fungus, viruses, and bacteria. And there's a lot more good bacteria, a lot more good fungus, etc. that are there. And it will be very difficult for us. So if you took a human being and killed all the good bacteria in that person is going to die, right? We have created this view about us that we are this one organism and we don't need the rest of the environment with us. I belong to the school where I think that you need the rest, and it is a good thing that there will be fungus, bacteria, etc. traveling with us, because that will be necessary for us to live. Without that,
from habitability point of view, I agree.
Yes, yeah,
but from the point of view of finding whether there was past life on Mars, this is going.
I know. These are two groups that are going to war with each other. That's it.
So maybe we wait till we find whether there was life on Mars earlier, and then we go for this habitability part.
The strength, what is your take on the high porosity being affected by, like, when you have these micrometeorite impacts, especially in a loner environment? So like, how, I mean, would you
see, that is a slightly different problem. So if you have to take care of micrometeorite, we now have to think of the entire architecture. So what type of bricks, what will be the shape and geometry. So there will inevitably be some impact, let's say. The fracture will spread the way we control it on Earth is one of the reasons we have separate bricks is one brick breaks, the other doesn't, because the fracture stops at the edge of the brick, wherever there is another glue material, right? So edge, basically all these interfaces is where fractures get arrested. So even with glass, for example, if you made glasses which have hexagonal glasses put together, the fracture actually stops at the interface. So here, whatever the small element is, I mean, it's not going to be possible to make it impact proof. The more porous it is, the more likely it is going to break. But if you look at the entirety of the structure, when you are making it, let's say, you can figure out what the binding material should be, or if you are doing interlocking bricks, then with interlocking geometry, we can make sure that when one brick fails, the other does not.
Maybe some coating for the outer surface or something in that direction.
Sure. I mean, see, holistically, I don't think there is anything that can stop, that you have something traveling at 100 meters or maybe like 1,000 meters per second. Micrometer is going kilometers per second. There's nothing that can stop it. But you can make it more durable by making it in smaller modular units so that one can fail, the other doesn't fail. And that's an important construction philosophy. And
Professor Alok, excellent talk. So I'm just wondering, like, okay, so Moon, we are having like many lithologies are there. So if any of these materials with a different treatment can considered as a binding material rather than bringing microbes from here to Moon. Moon or say Mars. Like Mars, of course, we have options, but in the case of Moon, like, okay.
Yeah, but on Moon, it's mostly sand. I mean, I don't know why you can't build through sand. You have to take some binders.
So I'm thinking of like this one basaltic fiber type of things which can act as a.
Yeah, but basaltic fiber is a composite that has to be manufactured. It's manufactured from basalt, but it is a composite that has to be manufactured. Far more complex problem. So you will have to take some binding material, and that is inevitable. You cannot go. There is no way that you just go there and have a fully circular economy where everything you are mining and doing everything. That's not going to happen, at least in the near term.
I know, but I got really excited when you started talking about astronauts and peeing on Mars and these bacteria like loving urea. What happens if you add a bit of urea to these bricks? Doesn't that help accelerate the process?
Yeah. So we actually so one of the things, because it's a
that becomes a good
because I deleted that particular slide where I described what we add to the bacteria. So we do add urea, we do add an extra glucose source, and then we have to make the salt concentration enough so that it's an isotonic for the microbes. So there's a significant salt concentration, and that comes from, these are very standard in microbiology, the kind of salts that they add for microbes. So that's what we do.
Right, okay.
Oh, yeah. So thank you, Alok. I mean, it's a very good first step. I mean, much more than that. I mean, we haven't done this kind of thing much in the country at all. And so I hope we get to fly this at some point.
Thanks.
Yeah. Sustainable way of making gas on Earth.
Audible? Yeah.
So welcome back. We'll continue the session. Yeah, thank you. So the next talk is by Ritu Karidhal, who was mission director for the Mars orbiter mission, the first successful mission from ISRO. She's now project director for the Venus orbiter mission. She has several years of experience, mission planning, operating. That's her expertise. And now she's the lead for landing site selection for our upcoming Mars mission, which is in a study phase. So she will talk to us about what drives landing site selection in terms of its engineering constraints and what are we looking for from the community to engage with us. Yeah, welcome Ritu. Yeah, thank you.
Thank you, Shama. Am I audible? Yeah, so good morning. So I think last 2 days and today, we have talked more and more about science and what has been done on Martian surface by the rovers and the landers. What is the future plans? It's on, I'm not audible? It's, oh, it's okay, yeah. So now we also from ISRO also we have this mission coming up, as Shama told, there's a Mars landing mission. And our study team, this responsibility is, to really see where to go and land. So landing is a very, very challenge part. And we had done in Chandrayaan-3, as you all know that we have landed in the very, very treacherous terrains, the south pole of, near the south pole of moon. And the most important part of any landing mission is to find out, where to land. The landing site selection itself is a very big topic and a very challenging task. And then when we talk about Mars, again, it's a very challenging. So today I will just, because there's no science, I'm not going to talk about any science. I'm only going to tell about where to go and what science we can do, how to, basically we are here, as a team, we are here with this science community to understand that which of the sites, based on our science objectives, which site we can go and land, because landing is not, is a very, very complex task. So I will be just covering some few part of the Mars. Everybody knows it. So for the completion's sake, I'll just go through some slides and then we'll see the engineering constraints and how we go about it. Yes, we know that Mars is a red planet because of the iron oxide, and some few important things which we should understand about Mars before going there. The way the day and night happens there is same like what we have on Earth. We have 24 hours of day and night together, and they're also near to 25 hours. And yes, it is away from, it is colder than Earth when we go, and it's 1 year, like we have 365 days is a 1 year. Here, there, it is almost 2 times of our 1 year. It's a 1 revolution period. And important part is why I'm covering, because when you select a landing site, when you talk about the engineering constraints, all these things matters a lot. And then seasons also, like in moon, we don't have any season or anything. It's like a very barren planet, barren moon. But then Mars is having seasons, winter, summer, sandstorms and all that. And then we know the difference with respect to Earth atmosphere is that there the components there are mainly major components: carbon dioxide, nitrogen, argon, no oxygen there. Yes, we know that, very limited maybe. And then the challenge part, when we try to land, the atmosphere is full of dust. So the peculiar part of the Mars, we have seen the very, very, but dust storms. Sometimes the planet is getting engulfed, total planet. Is it? It's working. Yeah. Can just check. Or maybe you can, maybe there's a null point here. You can, so we can, yeah. So this is what the very, very peculiar phenomena happens on Mars. The, full planet gets engulfed. Some seasons it is like fully covered with dust. So, to decide on landing window or when to land, all this understanding is very much required. And where the science community plays an important role is we know the dust patterns, but the prediction of the dust patterns where it becomes very important. So, where the science community and all that, what they worked on really understanding these things, then can they predict, and then can we have a good landing window? When at least we land, we don't have that season where the storms are there. This is a basic, just geodetic and astronomical comparison. Everybody knows, but it is like Earth, very much similar, and in terms of, in the sense, yeah, it's a spherical with some oblateness is there. It's not a pure spherical planet. And then its radius is almost half of Earth. And then G value is almost 1/3 of Earth. And then, as I told about the revolution day is almost 2 times of Earth, and the rotation period, that is a day on Mars, is almost equal to what we have on Earth. Important thing is obliquity, which plays an important role with respect to, reaching to the Mars, designing the trajectory when we go from Earth to Mars, because it is having also similar obliquity around 25.19 versus 23.4. So it becomes easier to go to that planet. And the other planet which have different obliquity, it will be having a huge propellant consumption or delta V required if you go different plane, where if the planet is on a different plane. But yes, Mars is almost near to the Earth ecliptic. So this is when we talk about also, in terms of northern part and the southern part of Mars. That is also very important to consider when we talk about landing site. What we understand, I think just some time back, the map was shown, which everybody knows, the topography of Mars. And what it shows, a very peculiar thing, that northern part of Mars is almost in a low altitude, low elevation, having very many places, there's a low elevations. And by the southerns, we find mountains and highlands. So that is what they call northern lowlands, while the southern is a southern highland. So this is what the map, I think it was shown earlier. So we can see the blue color, where it shows, the elevation goes below 0 with respect to the datum. And then we can go as low as -4 to -8 kilometers. While the southern side, we see that there's a highly elevated up to 8 kilometers. And so we will find the elevated objects. So these are some of the major missions which have landed. As already seen, that Viking 1 and 2, and then Mars Science Laboratory, and now Chinese also Tianwen-1. So till 2021, there are lots of landing missions have happened. And then we from ISRO, we are now currently planning to go in few years from now with the landing mission. So this is the places where people, some of the dots are showing where the people have landed. Maybe you can see that most of the regions landing is following in the northern part, yes, but and also the low elevation zone. These also all the blue in the previous slide. So these are the low elevation regions where people have landed. Because why? I will cover that, why this low elevation or low altitude regions are preferred for landing. And yes, this is some of the rovers which we have seen, and all these major of the landings have happened north of equator. So why this is north of equator? And as I mentioned, that north of equator is a low elevation or northern lowlands, means it is provides you a more sufficient height when we go for landing. So this, I will not go with Mars and lunar landing difference. Anyhow, we know there's a lunar mission, moon doesn't have atmosphere. Mars has, so totally a different type of landing we need to have. And it is not even, I mean, it may be similar, you can say similar to Earth, but it is not similar, more challenging because the atmosphere, the pressure is very, very low. So the parachute and then how we go about it and the actual terrain guidance, that's all different in Martian mission. So I'll just now come. So when with all these things, what are the real challenges or engineering, I will not say challenge, but what are the engineering constraints we need to consider and which we need to address when we are planning to land on Martian surface? Before, yes, and we go for deep space mission, we know there's a major constraint because even for moon mission, we know anything we can, the communication delay time is not much. We can even, any anomaly happens, we can always react to it. We can do some contingency recoveries, but when we start going deep into the space, the round trip time increases, and then it can go from, minimum can be 6 minutes when the Earth and Mars are the same side of Sun, and when they are in the, it can be maximum when they are at the opposite side of Sun. So it can be as 44 minutes of the order. What it tells is that we cannot have any real-time operations. The no real-time operations, everything has to be automated, whatever we plan, even the landing sequence, when we say, those landing sequence have to take place very autonomously. Nothing, by the time it lands, you will be knowing that it is landed only after 12 minutes or delay. So something we are seeing in the history, when we say on Earth, we are actually seeing what has already occurred in time. So this is very important to have, this is the major constraint. And then, as I told, the visibility, because, when we talk about the spacecraft to be visible to Earth, so we need to communicate with respect to telemetry, telecommand, and all those, navigation, etc. We need visibility, but there is a limited visibility. We don't get the visibility all the times, and as Earth moves, any station on Earth will not be able to see continuously Mars because Earth is moving. And on Mars, Mars is also moving, rotating. So landing place where you land, that and the station has to get in line of sight. That is a very, very limited duration. So that also we need to consider. And again, because the distance is too huge, we cannot have, unlimited bandwidth to download the data or, to do. So we have to be, that's why we say when we carry science instruments and all that, they have to be really, the way the science we get, the data has to be really precious, because the resources which we are using is very, very, precious resources. So the bandwidth available for communication, the data we get is also gets limited. And as you go very huge distance, the antennas become big and big, and you're pointing what is required to send the data is very, very get limited. For example, when we are the last Mars orbiter mission, it was only we have to maintain to looking towards Earth within plus minus 2 degrees of the, with respect to Earth. Any deviation of more than 2 degrees, you have lost the communication. And if you lost the communication, you can't do any operations, any science data we can't get on Earth. So that is a very challenging part to maintain the satellite within the line of sight of the Earth. So all these things, because when we talk of Earth missions, we know anything has happened. We have basically what we have omni antennas, like when you talk about low Earth orbit, when you talk about geo orbit, or even moon mission also, when we orbit, they have omni antenna. Anywhere satellite is tumbling or it is having any deviation, still we can do communication. We can recover the satellite. But then when we go to Mars or Venus or higher huge distances, this is not possible. If satellite goes into tumbling mode or it goes into any of contingency of the attitude deviation, we cannot do anything. The satellite on its own has to recover back. So it means the autonomy what you have to build in is up to that level that it should understand what deviation has happened using all the absolute star sensors or other actuators. It has to really drive the system. First of all, you have to detect where is the fault. Then that also has to happen like something called self-diagnostics. We can't see the data and tell because it has happened and we are coming to know only, let's say 10 to 12 minutes late only. So we can't intervene and see what is happening. So that has self-diagnostics is very important. And then once it understands some system is faulty, you have to isolate that system, bring back the new system and a redundant system and do the recovery and bring the whole antenna towards the earth. So that is the whole process. It has to be a fully autonomous process. And that is what we say that for this type of missions, we have to have full scale onboard autonomy. And the other important thing is when we talk of landing window or landing time or launch, this launch window also is very, very, it's not like every day. For example, if you talk of some remote sensing satellites, you can launch any day. Only thing what restricts you, what local time you want to launch. If you are talking about some sun synchronous application, some optical imaging and all that, you can do at a particular local time, but every day the launch window exists. If you talk about moon mission also, you can do every month, you can do an orbit. Landing maybe every 6 months, you get an opportunity based on the, again, constraints of other mission constraints. But when you talk about going to going to Mars or Venus, this, again, flexibility doesn't exist. This is windows come because they are like you call minimum energy transfer, something called that. So if we are going in minimum energy transfer trajectory, that opportunity comes for Mars once in 26 months only. So it means if we are missing this window of the particular, this one, we have to again wait for 26 more months to go and start our mission. And here's the other part which we need to see in terms of energy. The main source of energy is sun till beyond even Mars also. So, but when we go more into deeper into towards the Mars and then other side of sun, we get it's not coming. I think full slide is not shown here. Okay, this becomes the thing is the half of the solar flux only is available on the Martian orbit. So what we get is around 1367 watts per meter square. That is around 500 watts per meter square. So your solar panels, the cells have to be mounted such that they can produce with that less water, less flux. You can produce the energy, which is really meeting the requirement of whole system. So this is the thing which I just talked about, covering some things when we design a mission, what have to be taken care in terms of any landing mission or any orbiting mission to Mars. We need to account all these aspects. Now coming to the landing part. So landing part, when we say that Martian surface, what they do is that total by the United States Geological Survey, they have divided the whole Mars into 30 quadrangles. To just have some, like we have latitude, longitudes. So some of the latitude, longitudes they have covered and some quadrangles like they called Mars chart. So there are 30 Mars charts. And then focusing and with respect to when people, group of people want to study landing site, we also study starting from which quadrangle we should focus on. And even which quadrangle means that then again comes like, again, we go to science community and see, which part of this MCs are more, relevant to do science. So this is how they categorize it. And so total are 30. This I just to show how we go about it. Now coming, when we say that, okay, now science parts we will discuss. But then when we go and discuss science, it is also important that we should be able to land first safely. And safe landing should happen. and soft landing should happen so that we are safe and the instruments rover can come out. There is a place where it can rove around. What is the objective of the science it can meet, and then that is what is very important. So that is where your landing site selection plays a very important role. So apart from science, science is one part which really has to be given preference, but then is very relevant. But then apart from that, the where to land, where all these conditions are met with respect to engineering requirements, like for example, the slope. So suppose if you're designing the lander, which you have when it landing with even the crane also, when it lands, even within certain area, the slope has to be has to be less than this number. I will just come maybe typically it can be 10 degree to 15 degree, to make it stable landing. Then other part is when you land, you will need power. We don't like immediately on the day one, we don't go in the night landing and we struggle with the battery. We have to find a time when you land, you have a good sun illumination, you can do all initial operations, you can, normalize the lander and you can start the operations. So that is very important. On the landing day, while landing, you have a good sun illumination on that landing site. And again, important, as I told, the radio communication. So as I told, it is coming, for example, we have a station in Bailalu, that is IDSN ground station. And that IDSN station, we are trying to communicate to Mars landing site. But that visibility will not be there throughout 24 hours. Maybe it can be 6 to 7 hours, you can see that site. So you have to land the time when, suppose we don't have any relay satellite. So you have to ensure that we land when my station is visible to the landing time or at that time. So that is very important. Then coming, as I told, the hazards, the boulders, that also play an important safe landing. To ensure we do safe landing, we should see that what size of boulders the rover can withstand. Let us say the lower part of the boulder, what called the belly band of this rover, suppose should be 0.6 meters away from the surface. So we need to ensure that the place where it goes to land, at least the distribution is less. And this is one of the important thing for hazard consideration. Then this is also one interesting thing when you land. It's called something called rock abundance and its distribution. For Mars, this also plays a very important role because this maybe whoever done on this geology and all that, they maybe also see that the thermal inertia of the place, it is decided by how the rocks are, even the type of soil where you are landing, and the distribution of rocks. And thermal inertia is very plays an important role for design of the thermal system. So this also important when we consider the landing site. And yes, as not only that, the important again, the ground temperature variation, diurnal variation. If you see, the difference between night and day temperature is very huge on Mars. Some places is very huge. And then what is the actual throughout the life also, what is the atmosphere temperature, sky temperature, everything matters, because at the end, you are going to maintain the systems within certain temperature limits for them to work. And for that, you need power, you need energy. That is limited. So you have to also ensure that you don't go and land somewhere where you need huge power to maintain the temperature, or maybe if it is there, it should be a short-term operation and come back again. So those considerations also important. Then when you are landing, that is because I told the parachute will be playing an important role while landing. The velocity, that again here, wind velocity when you talk. So, what is the wind pattern? Because here when we do our launch, we can just, do some balloon experiment on the day or before the T-1 day or T-2 day. And we understand that what is the wind, what is that. But there we don't know. So what is important is the prediction of the wind velocity at that time. There also, again, lots of models. We are now looking at main reason for this community and science community coming together is to understand what is really available with us, the models what we have, and how to improve on those models, how to improve on the prediction of part of those models. Because when we go and land, this is all very important to understand. When we land, these things, criteria has to be met. And then as I told, Mars is having, dust throughout the life. When we go, the dust has to be minimum at that point. Even throughout the mission life, there are certain areas where you will find the dust patterns, dust storms, dust which has got accumulated on the surface is less. So we need to understand that part also. And yes, the science is the utmost significant. Once you land, you have to do science. So pardon, sir? I'll come to that. Yeah. So now the coming to the power system, as I told, power system constraints. What are the power system constraints? So when you land or when you go a particular place, as we see, because we have this 23 of obliquity. So because of that, we know when the sun is in the northern hemisphere, the night durations are huge longer on the southern part, and the day durations are less. And when the sun is in the southern hemisphere, the opposite happens in the northern side, if you go beyond 30 to 40 degree latitudes. Similar thing happens even in the Mars also, because again obliquity is 25 degrees. So we need to see that if you are above 30 degree latitude or 40 degree latitude, during 1 year of the Martian season, total period, when it is winter, let us say in the summertime, the number of the day hours can be as high as 16 hours. But then the winter days, it can be only 9 hours day. And out of 25 hours, only 9 hours day and others the night. So again, you will have to depend on the battery and the other systems, basically RHUs and all that. So this is, so we decide, okay, at least when we design the system, we decide I want only, at least let me say, average duration should not be less than 10 hours. So we have to limit maybe, let us say, to 30 degree latitude, where we can say the average duration is less than 10 hours. So this type of constraints will again play a role when you come which part of latitude or above, beyond this latitude I cannot go. Let me be within this latitude so that my at least average day hours is not going less than 10 hours. Like that, some considerations have to happen, because this is a very important parameter to ensure that sufficient power is generated for all the required operations. The similar thing, plot is only for when it is in the winter and the sun is on the southern side, just opposite of that. So southern means, southern sun is in northern hemisphere, summer will be more and winter will be again less on the same side. So this is the consideration when we go, and that time itself, suppose the design requires I should have a average 10 hours, it restricts itself that I cannot go beyond 30 degree latitude. Or if we have to go 30 degree latitude beyond that, you have to again bring out, yes, this is the science which is really, really giving you something very, different and unique. And that judgment has to be done really with all that resources. When we go, we have to carry that much. Then again, the lift of mass, everything increases. That what I'm trying to say, the justification for the scientific, science objectives and all that, and the landing site, they go very, very in together. So this is very important to consider. Now again, the important part is like we have the solar irradiance, as there is no much atmosphere. So what the opacity we get here on Martian surface, actually it is why it is very important, because while landing we are going to use certain optical cameras which will be seeing and on the terrain, and will take the image from the surface and do some terrain navigation, like what even we did in the Chandrayaan also. But then in Martian surface, this is basically driven by the opacity, what is there in the Martian surface. So the basically is nothing but the solar radiation, how much is reaching and how much is getting scattered and how much is getting diffused. So that is what it gives. And then in Martian surface, the optical depth, it can go as high as 0.4 to 3. 3 means opacity is totally opaque. The optical band cannot go and see the surface. So when we land, we have to ensure that whatever required for the camera system, that if we need, the camera has to operate within the 0.4 to 0.5. So we need to go the path of when the season and when the dust is not there, all that has to be ensured, and the opacity has to be within some number. Again, there also the dust storm prediction matters a lot. So if the prediction goes wrong and we find that opacity is this one, then your camera will not work. So that is what is very important. So you can see if the effect of opacity and other, not only camera system, but basically power generation also, because it tells how much solar radiation is reaching and how much cells are able to generate power. So if the opacity is, if you can see, if it is 0, we generate 500 watt power, let us say. But if opacity is 0.6, the power reduces. The maximum only you can generate 256 watts. And that too with the time of the day, from morning, early morning to evening, it will reduce. So this is also a big consideration when you want to land, what time you want to land, what and also which part of the latitude you want to land. You can see where the good opacity is there, whether or not, so that we maintain power generation as well. Then yes, other constraints for again filtering the landing sites, landing sites is sufficient solar power, as I told, but there also play a role of the shadows. 2 minutes only. Oh, so I will try to go. Oh, I will go fast then. Yeah. Yeah, so it's not only solar power generation, the shadows also play an important role. So you should know the topography of the place, I mean, up to with the available data, and see that, you know, the shadows are not falling, long shadows or the horizon shadows of, you know, tall mountains or certain things not falling on the, at least on the lander, because lander is the thing which is going to generate power, even rover also. So rover also, when we do path planning, we ensure that it is not going to the shadow regions. So that is what is important. And then yes, the nighttime survival, the minimum dust degradation of panels, these all becomes a very important part of designing the power system. So here why it is important in this community to discuss that we need to really understand the dust pattern. Other things, geometry, we know all that we can do, but this what is the most random and unknown and, you know, difficult part is the dust. So the dust prediction becomes very important with respect to, you know, seasons, the landing locations, and that is how even to decide on landing window, landing place, all that plays a very important role. So models which can do that, that is a need of the, I mean, I know maybe people must be working on it, but this is what something which really needs to get addressed. Then I will go fast as Shyama is telling, not much time. So as thermal constraints are there, so thermal coming from power to thermal anyhow we know the external Mars environment, that will play an important role. And again, internally what type of power dissipation is happening within the system, within the thermal lander. So important, again, the ground surface temperature, if you see here, again, this temperature plays an important role, because as I told, it should not be too much variation. The variation between day and night has to be lower. Then only it is easy to design a thermal system. So albedo also should not be high. Again, it will create a more variation. So it should be less than 0.18. This is a typical number, but yes, the thermal system designer can design even for higher also. So this is very important. Similarly, the atmosphere temperature also. The actual temperature only, the density is also depends upon the temperature, and density also plays a very important role when we design a, you know, a parachute, and we know this much limit density has to be there for getting that landing time or before the just landing time. So this is also important, the temperature of the landing site at the landing time, and even further to maintain the thermal parameters. Then sky temperature, that also is because the radiative part, you know, the radiative part comes and interacts with the lander. So this is also the way you design the thermal radiators on the system, how much it will radiate, what is expected. So that design also very important. And then yes, the ground, as I mentioned again, the opacity and the ground solar flux, which is again very important part when we talk about the opacity. So this is for example, in the winter you find the ground flux is better than in summer, because summer, as I understand, because of temperature, the density again increases, it reduces the opacity, while in winter you find the better opacity, I mean the solar flux. So this is also needs to be considered when we're trying to at least a landing time, and also if it is possible, the locations where we can see that the effect is less. Then wind velocity, again, as I told, the important part is, you know, when we do the average wind speed, when we design the system at typically acceptable wind speed, because there the speed can go as high as 32 meters per second during the dust storms. At that time, if you go, your parachute will not, your landing will not be a successful landing. So what is tolerable wind speed which we can survive, or lander can survive in terms of, so typically acceptable number, 16 meters per second. So again, the prediction of the wind speed becomes very important. So when we go, what is the real wind speed? As told is thermal inertia. So basically thermal inertia means at which rate the surface temperature, the surface material change the temperature, and then that again, if the loose dust we have, the loose dust looks like it is having low thermal inertia, it will very fast will heat up and very fast will cool down. That is not good for a thermal designer. So there is a constraint that the thermal, then when we talk about, if you have some sites, it's not coming, but here the rocky surface and nearby, if there is some, distribution of rocks and all, they will maintain your thermal inertia. They will have a better, higher thermal inertia than the loose soil where we have like a desert. If you go, there is something very loose, thermal inertia is very low. Thermal design becomes very difficult for that place. So we need to see that, okay, it should be safe also, but then it should have some sort of, rocky distribution which can really maintain the thermal inertia within a limit for that landing location. So that is also becomes an important consideration. And yes, parachute landing, as I told beginning itself, people have gone basically in the northern lowlands. Why northern lowlands? Because it offers you the places where the elevation can go as low as 1 kilometer down to the, below, less than even 1 kilometer from datum. So it provides a big vertical column for parachute to land. So if this is what is very important. So that is like enough, because once you go down, density will increase, but you go down, you should not crash. You should have much place to vertically go down. So that is why the northern hemisphere was considered more and more, because it provides locations which can give you low elevated surfaces. So this is typically, if you see, many people have gone with elevation less than 1 kilometer. The many sites, if you see, they have gone with this much. Then lander stability, as I covered, is not, again, I'll not go through. The slope matters a lot. What type of slope it should be, the boulder size and the rockets, rocks. And yes, atmospheric parameters, as I mentioned, all this density, the horizontal wind velocity, because it is in moon, we only saw horizontal wind, horizontal velocity and vertical velocity, how to maintain that is what. But here, it is not just alone that. Wind also plays a very important role. So what should be the minimum wind velocity when we go land? So that is also an important parameter which needs to be considered. And for landing, again, as I told, for terrain-based navigation, as I told, 0.6 may be a better number for power generation, but for some cameras to work, it has to be less than 0.45 for some number. So it is the cameras have to be also designed for that purpose. And other part is radar reflectivity, because you are going to use radars which are going to measure altitudes, the velocity you are going to derive from that. Radar has to have good scattering, where it can, radar scatter can come, and then you can, sensitivity is good enough, accuracy is good enough to get that. So where your, and also when they say, when rover is landing, the bearing, the soil should bear the load of the rover, it should not sink in. So all those things, the trafficability of rovers also, when we are going the slope of the side, when we are going, rover is roving, what is a typical slope you are getting? So all these play a very important role when you are going to select a landing site. Already I covered with Earth. Earth communication is important in the sense for IDSN, as I told, it will be minimum, it can be a mean duration can be 6 hours only. Maximum it can be, suppose my IDSN and the landing site is just, matching in line of sight, it can be 12 hours. Because if landing site is rotated and gone one side and IDSN is on the other side of horizon, then it can be as low as, mean can be 6 hours, or it can be even go to less than 1 hour. So this is how the communication, so people are planning, when you have to have a continuous visibility, you need to have a relay satellite like geostationary we have. There also aerostationary orbit is there around 17,000 kilometers. You can put a satellite, you can relay the data from that satellite. Again, that is, so this is, and the important point which I want to just cover here, when we talk of landing, the science, theme, science, all that, we need to know what area we should cover for the particular science theme, correct? And but when we say that this area we need to cover, we also should understand when we land, there will be some landing errors. So when we decide on the science and the objectives or the theme, we also should consider that there will be some landing errors. So my science should not get compromised, or whether I am having a science, even if I do this much of error also, I'm not getting compromised. So the contributors can be, simple, like when we enter, how accurately you are entering. The position and velocity accuracy matters. You are going to around 200 millions of kilometer distance. You are doing ranging, Doppler, and finding the position velocity. We don't have GPS and all that, their accuracy. So we have to depend upon the navigation systems, which is right now available with us. So right now, the Doppler, ranging, all those things, the accuracy of those parameters play an important role when you're going to land there. Then again, sometimes it matters whether I'm doing guided entry or unguided entry. So if it is guided, then again it will ask for some resource requirement on the lander, but then it will give you a control that the parachute I can control with what altitude, with what velocity I need to start parachute landing. So this point I can control at least. Then that error will be different if it is unguided. And then, yes, this is the wind conditions will matter when we are doing in this parachute phase. And then when you do for final landing, when terrain navigation comes, and then navigation, total guidance and control, so all the NGC errors. With all that, we have seen, some of the statistics which is available right now with Mars Pathfinder. It was unguided, and the ellipse was around 130 kilometers by 27 kilometers. So your error can be as high as 130 in major axis direction and 27 kilometers in the other side. But guided entry, nowadays people are going with guided entry because suppose you want to go a particular crater, which is only just a few kilometers in size. I can't afford to go away from that. So that you have to have a error ellipse lesser. So you go with guided entry. And people have mentioned, like in MSL, it was around 25 by 20 kilometers. In Mars 2020, within 10 kilometers, they could achieve that. So this is also, but this again, as I told, requires resources. It requires, lots of on the design aspect. This is okay. Again, when we cover all those points I have put in the table. So what should be latitude, elevation, ellipse, slopes, rock height, radar reflectivity, surface winds, all these play a very important when we design. We do all these parameters based on the requirements of the lander or lander design, what we have, and we put these parameters and then see that which of the site is, giving a better number. We prioritize or rank those sites, and then along with science, themes, we combine and then see which place we have to select. So this is and we all do this with available data sets. When we do all. So what I understand for our topography, we have good DEMs available and all that. But when I talk about these models where we have to do dust prediction and all those opacity, atmospheric modeling, this is where we have to really get. And as Priyanka, who's now handling MLM, she knows that we need to really get good models where we can do a better understanding where the landing site has to be real, where engineering constraints will be met. So those things play the science team really has to gear up and, get us those things so that we can find a good site. So this is various science I will not cover. You have various themes, but those themes again, which has to be prioritized also, because this again depends what type of payloads I am going to put on this lander or rover. That is a very important thing. Just like that, any payload or instrument cannot be put. So what is the science objective? What is the priority theme? Based on that, what payloads we have to put, and based on that, what site we need to select. So our theme is suppose maybe we prioritize the themes, and then again engineering constraints come into, as I mentioned there, and then seeing the both of them together, selection of sites and the ranking based on the constraints and the landing area size. So this last is left only the science team has to provide this atmospheric model with very, very, high fidelity models where we can, do a prediction sort of thing also, not just observation and analysis and all that. We should be able to do a prediction modeling and covering the thermal maps, dust storm predictions, season which change with season and time, the opacity, how it varies, the rock abundance, the surface soil characters, all these play a very important role to really get a good landing site to land on and meet your requirements. Thank you a lot.
Thank you, Ritu. Questions?
Yes, sir. We are on the process of selecting. But again, as I told, science teams play an important role. Engineering, again, with some available data, what I showed, some MRO data and all that we have. We have done some engineering constraints But then science is also important. So where we say that MC I told mass chart, that mass chart, if I select whether real science is there or not. So that they have to come out with the, so we say, yeah.
No, it's more difficult for scientists to reach a consensus on what is the priority, I guess, than the engineer. So yeah, that's where we are.
Thank you, Rituji, for a wonderful talk, and it tells me how important the engineering aspect is behind a mission.
So I want science team to understand, and then both of teams should go together. Sometimes they get disconnected and we don't get good science.
Yes, yes. So I just wanted to know from the ISRO team, everyone, that what we have already achieved in Chandrayaan landing mission and how much technically difficult it is going to be to take a jump from what we have already landed versus, of course, the Martian regolith and the dust storm is important, but beyond that,
this is what difference. See, the challenge is your again the parachute in the low pressure conditions.
So what are the major environmental changes which you are going to?
There's no atmosphere in moon. There's an atmosphere, there's a wind, there is a dust, there is a a low pressure atmosphere. This is the biggest challenge. At least moon, there's no other external element to interfere. You have to just see your thrusters are performing well, you can go. But in Mars, there are external factors which will disturb your trajectory. Pardon?
The lander and the declination, the inclination.
That also, slope is also important.
As in, that is something you probably would have already considered on
Yes,
the lunar
yes, we
surface?
have considered. Now, whatever MRO data is available and high resolution data, that DEMS is not an issue. I told topography and DEM is not an issue. Issue is the other three parts.
With respect to LAM, if we compare Mars and Moon, atmosphere is the major challenge here. Because now many landing sensors and all we have developed, but here in Mars atmosphere is there, and that too very thin atmosphere is there. So in Moon we landed in 20 minutes, so we had enough time to judge also our guidance to control and react. But here our landing has to happen within 7 minutes, and in that, since atmosphere is there, we have to take care of heat. So that is why we are planning with parachute and aeroshells. Parachute also is a major challenge here, as ma'am said. Here we have to land with the almost 2 Mach speed. So that parachute development itself is a very big challenge here. So all those new challenges are there.
Supersonic, what you call supersonic
parachute.
Yeah, that's what I showed. Without that, you cannot control fully. Yeah.
So these are all new development with respect to our earlier moon landings.
Yes.
Any questions? Students out there?
More robust because more perturbing elements are there.
Probably a question for Steve here is, of course, we've landed, NASA has landed. So how did they design it for the dust storm, etc.? Did you go for the max speed velocity, or did you actually do that modeling? And how can ISRO take that data and design?
I'm not quite sure I can answer this. It's a little beyond my particular expertise, but there's always this effort to avoid known global dust storm seasons and times of a year. It's harder to kind of guess at the particular opacity during a given landing period. But as Ritu was already saying, there's a summer, winter known sort of atmospheric conditions that there's been years now, thankfully, of monitoring of Mars atmosphere over time and years to recognize these seasonal patterns depending on what hemisphere you're in. So all of those sort of pre-existing pieces of information are brought to bear for any given new Mars mission. We're not going to go at this time of year in this particular place. So that's all I can really say.
Meters per second, 16 meters per second. Is that what is designed typically?
Yeah, one very major point that he highlighted was now we have certain data, certain patterns and seasons where we can plan. Other thing is the spacecraft or the lander itself has to have its own capability to either have some mitigation for dust or have an inbuilt units which can nullify the effect. For example, the dust mainly impacts the energy generation here. So if there are mechanisms where we have an alternate source of energy generation, that something can be done and the missions could be more long lasting. And also there are missions who have succumbed badly to the dust storms.
Yeah, they have just jittered and then dust was gone. So that was a jittering part of it, yes.
But some missions, many of the recent missions, they have actually outperformed also. So that is something which would be considered in ISRO's landing mission probably. Thank you.
So, I mean, I understand that this is still a work in progress. We have to
yes.
sites.
This workship is one of the parts of it.
But so one way to know, obviously the wind, dust, as you said, those information will be important. But are we also predicating our final decision based on where others have not gone? For example,
yes. That is what is also our main criteria. We should not again go where others have gone. We should select the sites where, it was uncharted area at least. So that is also consideration, yes.
There was a discussion on going to the same place again.
Yeah, but again, science people should not tell, no, I want to go there only. So it all depends upon science.
And could come up in future because subsurface is still, you get a lot of, I guess that's what I understand at least. You get a lot of pure things inside.
But you are having drilling instruments and all that. So
the core drilling and all would definitely be.
That again decides that what science and then what instruments you should have that will play.
I will just add on to this thing because we had discussion about core drilling. We had discussion in terms of places where you have maximum erosion. So now there are locations where it's a kind of a dynamic system because we know that there are waters, there are things which are flowing. So now is there kind of a win-win situation if you land up in such regions where you have more exposures to essentially not drill, but essentially do nice photography and imaging.
Yes.
Which is not being done so thoughtfully in terms of previous expeditions. So
that should be a consideration, yes. Okay, thank you a lot. Thanks.
Thank you. So our next speaker is Vivek Vardarajan from Uncharted AI, which is a Bangalore-based startup. Thank you, Vivek. Really looking forward to the talk.
Sure. Sure, it works. Work. Hello, everyone. Can you hear me? It works? Okay. Hello, everyone. Good afternoon. I am Vivek. I am the co-founder and CTO of Uncharted AI. It's a great pleasure. Thank you for inviting me here and organizing this great group of talent here who has put together great thoughts and presentations together. Thank you, Professor Ramanathan and Professor Martin and Shama, ma'am, everyone. Okay, so what I wanted to talk about today is basically how do we build autonomy, right? Why do we need it in the first place, right? Space is full of challenges, as ma'am was introducing, right? From ISRO, Ritu ma'am, right? There's immense amount of challenges that we need to go through if we really want to get to somewhere other than Earth, right? Earth is best. We know Earth the best, right? So I will start by, I'll start by giving you an overview of my career. So I started my education here in India, in Tamil Nadu, then moved to Germany, did a master's in automation robotics, PhD, postdoctoral fellowship in Canada, and now I'm building my startup here at IISc Art Garage, which is Uncharted AI. So in terms of experience, I've worked on Canadian Space Agency missions, European Space Agency missions, NASA JPL during the DARPA Septennial Challenge. Also, I led
I've led teams at ESA Challenge and other space analogs. So overall, I stayed very close to the space ecosystem, and I've built systems for space, and also have been part of several analogs. So before I get into my talk, I just wanted to show this video. Credits to NASA. The orbital launch sequence of Perseverance. So we see a launch vehicle takes it from Earth. A lander takes it onto the surface of Mars. The amount of effort, engineering effort, and the money that goes into this is immense. It's fascinating to look at the possibility of looking for life and other science objectives are immense, right? So this small piece of equipment, getting it to the surface of Mars, costs an immense amount of money, right? So this is just a timeline of the types of robots that have been launched to space. I'm sure everybody knows. Mars, we look for several science objectives. We want to know where life is, whether it did exist or not, future life did exist or not, like past life did exist or not. So I just have a thought here. So why do you think like we only have like 45 kilometers, for example, take opportunity during a period of several years? We only were able to achieve 45 kilometers. Does anybody have any thoughts on why that is the case? I mean, of course, except for the ISRO people, right? They know. Yeah, so exactly. So, right. So the problem is you have to drive. You have to have communication with the Earth. So you need to be able to, like, all of these robots are like the rovers that we are launching are basically, you need to tell them what is the route it needs to take. You need to upload a route. And then you need to tell them this is the sequence of points that you need to visit, right? And then interact with it. And each of these iterations take 20 minutes on Mars, for example, right? So you send something, you upload a mission, it takes 20 minutes. I mean, 40 minutes, 44 minutes worst case, 6 minutes in the best case. So all of this combined together takes immense amount of time, which leads to like we can only drive 45, 50 kilometers on several years of traversal, right? Which we could do in a few hours on Earth, right? So what is limiting it is basically like the sheer amount of distance, right? From a roboticist point of view, right? I'm a field roboticist. So from what I see, it's 40 minutes back and forth. And I mean, it changes, of course. It's just some approximated distances. So we actually basically need autonomy. That is the point of me introducing all of this, right? So we actually need autonomy, but autonomy actually, if you want to deploy it in very unstructured environments, it's not especially ready, right? So we have several factors that we need to look at, and we need to be able to improve them if you want to actually send it to an extraterrestrial planet. So we're still in the realm of being able to upload a sequence of mission and execute it on the robots, right? That is how we've been doing missions. So what we want to do is to be able to build autonomy so we can actually get into lava tubes, subsurfaces, which are the most interesting science spots. I'm sure you guys will be very curious. Like lava tubes are an excellent source, are excellent points where you can find signs of life. And we've not been able to do it because the terrain itself is very unstructured. Like you look at caves, it's very unstructured, uneven. What we want to be able to do, like what we want to be able to achieve that is we want traversability, not just rovers, we want various mobility platforms. that can actually enable motion into very unstructured terrains, subsurfaces, and also even if we have rovers, if we want to actually traverse long distances, we need autonomy, right? So this enables several possibilities, even on Earth and on the surface of Mars and Moon, right? So why this is hard is because when we go in caves, there's no GPS on space, of course. So we do not have any form of localization. The robot has to know where it is, build its own map, build a world model. How is the world structured, and be able to localize itself in the world, traverse it, navigate itself on this world model that is created, and actually execute these actions, right? And communication is extreme. Like in space, it takes several minutes to actually talk to the robot. In caves, it's very harsh. You can only go a few meters. You need to drop communication relay nodes, or you need to be able to talk to the robot to actually know what is happening, right? So all of these environments are harsh and highly challenging traversably. When we look at multi-robot systems, it obviously, like when you have one robot, you can carry one scientific instrument. When you have multiple robots, you can have a combination of scientific instruments. One robot could have a robotic arm that can pick up samples. The other can actually have a spectrometer that looks at various types of signatures that you want to look at. So a combination of robots will actually improve, the heterogeneity will improve your ability to do various types of science missions, and also do better in terms of time-sensitive, large communication delay situations, right? So when we look at autonomy solutions, there's two types of autonomy solutions: classical methods, data-driven methods. This is basically some theory. I don't want to go too much into it and bore you, but the idea is you have perception, planning, and control in classical methods. It takes observations, produces actions, and you have modular components that enable you to achieve it, right? So there's a specific problem that you're trying to solve, and you solve it using a specific method that is grounded on the theory that we know. But whereas in data-driven methods, we just use a collection of data, just compress it, feed it into a neural network, and be able to train an end-to-end observation to action model, right? So there are advantages and disadvantages of doing this. Performance, flexibility, qualification, you can have better performances in certain situations and the ability to be modular when you have classical methods. Of course, if you want to design a perception system, you need to have domain expertise, be able to understand the theory behind it, and design them, but it does not generalize that easily. And the same thing with data-driven methods. You have several techniques you can, like domain randomization and so on, that can enable you to train across various terrain, slippery models, friction parameters for robots. And you can, basically, if it doesn't work, you add more data, keep adding data. And there are disadvantages, like if you go out of distribution, you actually cannot predict, right? You have to add more data in that specific distribution to be able to train these models. So the solution here is basically to have a combination of these two. That is what we found to be very useful in autonomy, right? We, especially for these quadrupeds, walking policies, control algorithms, so some of them are very good with data-driven methods because this policy that you see here was completely trained in simulation, was transferred onto the robot, and it works right away. Zero adaptations, right? So in a similar way, like if you have certain things that are very good with data-driven methods, you can basically combine these two, and in our autonomy, we basically do that. We combine these two modules together. So if we look at our autonomy, right, we have various modes of sensing, LiDAR, and cameras, IMUs. So we also have a specific sensor, like a science sensor. It could be hyperspectral cameras, GPRs. We work with various payload modules, depending on the context of the mission. So the perception basically takes LiDAR inertial, like LiDAR scans and combines it with visual inertial odometry. Basically, we have a specialized system that can achieve sub-centimeter level accuracy. How we do it is we use a special Bayesian network formulation, a probabilistic model that chooses and moves between LiDAR and visual based on the accuracy, like based on the covariance that you observe currently, right? How is it visually degraded? So don't trust vision much. And then it basically assigns weight on a 0.1 second window and then chooses between LiDAR and visual. So you see an example of the perception mapping system, a LiDAR mapping system that sequentially progressively goes and constructs a map of the environment as the robot moves around. So in terms of planning, this is a local planning. If you see, this is the kind of planning that you see on Perseverance rovers and the newer generation of rovers, right? Where you upload a sequence of mission and then it basically navigates on a local scale, looks at the terrain characteristics, looks at the surroundings, avoids obstacles, but still it only looks at the immediate environment, it cannot look at the overall global scope. So what we build also is something called a global planner. I'm sure some of you know, where it's a sample-based planning, information gain planning. So as you see there, it's basically looking at points that can be visited to maximize information gain. So it's looking at terrain characteristics, the overall, the environment itself. It's trying to maximize the information gain on the environment and moving. This is a Canadian Space Agency's Mars analog site that you see here, right? And in mission planning, the goal there is basically we select behaviors based on the type of overall context of the mission. The robot needs to know how much battery it has, needs to get to a charging station on time or a stop if it doesn't have sufficient battery before it dies out. So all of this, we have behavioral modules that basically tries to select and coordinate between robots as well as the human operator, right? And we also have control actuation because we are robot agnostic. We're trying to build something called unclouded foundational intelligence, which is basically a robot agnostic autonomy that we want to do. Unfortunately, the video doesn't play, but the idea is like we are also building something for control and actuation of various mobility platforms. And in terms of communication, we have a multi-robot network that can communicate between multiple robots, coordinate, exchange information, dynamically create routes, and also heal routes, remove routes if nodes are going out of the network, right? And also we have gossip-based information propagation. Robots send information as gossip broadcasts, and they know each other, where they are, what parts are being explored, so they can parallelize all of these exploration missions or the mission itself, right? So this is one of the missions that we did. I'm going into a bit of the field missions that we have done. So this was a mission end of last year that we did at a lunar analog facility. So this is not an autonomy mission, but we built all of the basic components. So this is a lunar analog facility in Germany called Luna, which is a warehouse filled with regolith simulant, EAC1 simulant, 1A simulant. So basically we have a rover that goes, identifies sites. We teleoperated, it's not autonomous here, but the overall mission control and everything was designed from scratch by us, including the rover and a beneficiation station that basically takes in the regolith, sorts it into 3 different particle size distributions. So you see here, the robot is basically taking in the regolith, storing it on the onboard bins. So it can take it to a beneficiation station, sort it into 3 different sizes. Like basically if you look at the types of things that robotics that we do and what you guys are doing, is like we take your science things and try to bring it to reality, right? So like Professor Alok was talking, like we can bake bricks, we can make various other things based on particle size distributions. So Here, the idea was to show the sustainability of 7 astronauts over a period of 30 days to produce oxygen, right? We want to show that we can extract sufficient amount of regolith to break the regolith into using into oxygen and other components using molten salt electrolysis to show that you can sustain life support for 7 people, right? So this was compressed. The idea is to have like an analog and compress it into a 2.5-hour mission. So if you can extract a proportional quantity of that and sort it and prove that you can manufacture oxygen, then we can basically sustain life, right? So this was an invitation for a tender. We competed in the tender and we built all of these systems from scratch. We excavated 12.5 kilos and achieved an accuracy of 70% and large dust mitigation because it was meant to be operating around humans, right? So this is the beneficiation station. The robot sequentially goes in process, excavates. As you see, it's in reality, communication is not great. This is a video that was recorded from mission control. So you can see that it goes out, comes back. So in reality, that is the case, right? So when we operate rovers, in space, it's even more harsh, right? We have a 2-second delay if you want to operate it from the moon. So this might not even be possible, right? So this is another analog that we did with the exploration planner, the global planner that I introduced earlier. This is a fully autonomous mission with 3 robots in the Canadian Space Agency's Mars yard. So you can see the 3 robots are distributing in the environment, trying to acquire a map of the environment, and they're coordinating to do it in an efficient way, the most efficient way, right? And this is one of our robots here at Art Garage. This is some of our autonomy components in action. So you can see on the left, the robot is moving. On the right, you see the world model the robot is building. The points that you see are the possible points that it's choosing for global planning, candidate points, and then it chooses a path and then that traverses that in the world, right? It's fully autonomously doing all of this in conjugation with the information that it acquires from perception, right? So the robot basically constantly goes continuously planning information gain, as you saw, and that's the overall idea of this video that I wanted to show you. So this is another test of our localization system indoors, just to show that it's fully GPS denied, right? We can achieve a sub-centimeter level accuracy with the robot moving in an indoor environment with the map you see, and both in the Z axis and in the XY, we can achieve sub-centimeter with accuracy with up to 1.5 meter absolute translation error per kilometer. So we can basically rely on these maps to be able to navigate a few kilometers, right, beyond which it degrades. But as long as you have loop closures, you can still be able to sustain with these onboard mapping and localization. And this is at the Art Garage facility at IIC here. And these are some of the other missions that we've been part of. I've been part of it as a part of my career. Some coordinated missions, the earlier video that you saw at the Canadian Space Agency. And also we've done cave missions with flying quadruped, also wheeled legged robots in complete icy environments as well, right? We've had caves, glaciers. We've gone into like as harsh as possible environments to be able to test our autonomy components, right? So this was earlier during my postdoc, this video, as you see. So currently, this is the mission that we are working on. So I just wanted to give you a glimpse of it. I don't have real pictures for all of this. we have a system that we're building. I didn't want to put it before it's being built, so I put AI generated images. So it's a drill unit, a sample collection chamber. We can drill up to 1 meter under the ground. We're building a system that can build drill meter in mining environments. This is for mining customers we're building. We have some pilot customers that we're working in Australia with Uncharted AI in mining mainly. We eventually want to bring this space aggregated and bring it to space, right? If we can do it on Earth, we can eventually deploy it to space. So the idea is to be able to drill at least 1 meter under the ground, collect samples, and we have onboard spectrometers to analyze the mineralogical composition and provide real-time feedbacks on the mineralogical composition, pack these quantities of soil that's been collected, because there's A horizon, B horizon soils. We discard the first 50 centimeters and collect the next 50 to 1 meter. We want to basically get to 500 grams to a kilo of sample and pack them into specialized bags, geotag bags that can be sent to labs for further validation if something hits out, right? So this is the mission that we're planning in June in Chhattisgarh, Maharashtra. So we have a sample mission that we're working with. It's a grant from the government. So we are working with ISRO, GNRDCC, it's Jawaharlal Nehru Institute of Aluminium Institute. So we were for bauxite exploration in Chhattisgarh and Maharashtra. So this is a mission that we're doing in Chhattisgarh. So basically, there's a grid of samples that we want to collect in various regions of possible mineral sightings and analyze it, drill up to 1 meter and collects and analyze it real time, right? So in the long term, my research vision is to build robots that can be sent to space. This is the first multi-robot mission that NASA is working on called CADR. Some of my colleagues work there in this mission. So basically you see 3 robots that carry ground penetrating radars, coordinating with one another and creating maps of the subsurface, right? So I basically want to work on missions like this. My specialization is field robotics and multi-robot systems. So working together and sending these equipments to space is been my passion, and I want to continue doing it, right? So overall, there are several problems that exist if we really want to do this. We need decentralization. We need knowledge representation between robots to minimize the amount of information like humans do, right? We can efficiently communicate in few words and make others understand, but robots will have to send in gigabytes of maps to be able to synchronize maps. So how do we effectively represent knowledge on robots, right? So how do we interact with these? When you have multiple robots, you cannot teleoperate each of these robots. Like it's NX, the complexity. So you need to be able to have new modalities. How do we interact with them? So this is my long-term research vision. So I look at building things that can enable us to do these things more efficiently, right? So open challenges, failures are inevitable. So you need to be able to know how to tackle them. So that is, this is one of the recovery mechanisms that I did during the DARPA Septarian Challenge. Basically, you see the robot fails, falls down, recovers itself from this fall, and then fixes all its localization, estimates and planning estimates on board. It will execute a recovery mechanism and then recover itself. It actually fails. It fails even in recovery a few times and then succeeds at some point. So that is basically the idea, right? So it tried recovering, it didn't succeed, then it tries again. So that is the kind of mechanism that we got to incorporate when there is a failure, right? How do we autonomously do all this? Like, how do we recover from these failures and continue the mission, right? So that is the goal. That's what we want to do in space. Like, if you really want to deploy robots in space that are autonomous, and semantically understanding the environments, representing knowledge, and generalizable planners, right? So those are the things that I constantly work on to improve these systems. So we are Uncharted AI, and we are looking for people and collaborations as well. We are very young. I just moved to India a month ago. So if anybody wants to collaborate or work with us, please reach out. I am always open to looking at new collaborations. So this is one of another deployment that we did. So you see the kind of unstructured terrains these quadruped robots can tackle. This is how caves are and mining environments and unstructured environments are. So how do we tackle them? So reach out to me if you have questions. It's better Vivek at Uncharted AI or my co-founder Pradyumna at Uncharted AI. If you want internship opportunities or even you want to work with us full time, we are open. We have several open positions. Or research-wise collaborations, grants, or working with us. Thank you everyone for the opportunity. If you have questions, I'll take them.
Questions?
When you claim for 99% dust mitigation, what do you do?
Sorry?
99% dust mitigation, I saw some.
Oh, yeah. So
what do you do?
Basically, when you process regolith, the regolith has several, like a large composition of 100 micron or less particles, which just basically creates fumes. So if you want to process regolith into various particles size compositions, it generates a lot of dust. Like even excavation.
So how do you mitigate that?
So you have to basically have electrostatic shields, covers, all of those to actually, we did some of those to mitigate dust, and we got a very large score for it because the trick that we did was we excavated very far away from human zones. They had a human zone. So that's why we have a very large score for dust mitigation. So they measured it by putting markers like adhesive markers, and basically if you get fumes, they go stick in those stickers.
Also, are you looking for more than 4-leg robots? The 4 legs sometimes double.
4 leg is already very energy. It's not very energy efficient at all. So leg robots are least energy efficient. That's why we look for wheel robots, right? To be more energy efficient. So bipeds are somewhat, it's not the best configuration. So if you add more legs, it'll be more energy consuming. That's the only disadvantage. So because you have to actuate 4 legs, so that creates a lot more energy. Like you need to spend more energy.
Yeah, that's just one question you mentioned about 70% of accuracy. What is meant by that? And also, the robot itself, I mean, is it able to understand its, as you told, survival mode? When you talk of its energy is losing, and then how it survives with the low energy mode, or it should survive till it gets the more energy or somewhere. I mean, that survival modes also are built in.
So we actually have, we incorporate things like behavioral trees, or like, which are very analogous to state machines, right? Basically, it goes into, like for us, we are currently looking at terrestrial cases. So we have charging stations the robot can drive to charge. So we trigger those behaviors. We look at, so whenever the robot is going to a point, it always keeps track of the path that it has to take to get to this charging point.
Retraces back to the original point.
Original point, it keeps track of that. So it's building a graph.
So it is built in?
It does build a graph of the globe.
And then you have created anomaly and it has come back to its charging station or something like that?
Yeah, exactly, ma'am. So basically it comes back to the charging station. So in the case of space rovers, we have to hibernate.
Very important.
Sorry, ma'am?
For space rovers, that is a very much important aspect.
You're right. Definitely. So because we usually consume more energy than we can actually produce most of the time. So we basically hibernate, stop operations, shut down all possible things and just hibernate for a fixed amount of time under sun.
What is 70% accuracy meant?
Oh, so that 70% accuracy is basically the particle size distribution. So we had to sort regolith into 3 different particle sizes. Anything below 100 micron 100 to 500 micron, anything above 500 micron. So how accurately we classified those particles, they actually, for all the 15 kilos, sorry, 12.5 kilos that we extracted in 3 different bins, what is the accuracy that we achieved? It was 70%. So that was...
Okay, good work. Keep
Thank
it
you,
up.
ma'am.
Yeah, just wanted to know, during your trials and probably the operational use, have you encountered any physical damages, and do you have a healing autonomy kind?
So always.
How-
Robots fall
Yeah.
all the time. Like there are edge cases, corner. Even during the East Side Strike Challenge, the last thing that happened was the rover flip over altogether, because we collected more soil, more regolith than we can handle, and then we started going on a slope, and it just fell over, tipped over. So it happens. Like you have to be very cognizant of these things and incorporate mechanisms. Think beforehand. It fails. There are edge cases. Even that's why we are not able to even deploy fully self-driving cars, right? There are edge cases. Like 99.9% of the time it works. 1% it doesn't work. Is it good enough? Can you put your life in front of it? No, right? So that's the one edge case we need to be able to catch and handle, right? So that is one of the big points of research that I focus on as well.
Okay, are you also into introduction of some novel materials with some healing capacity or anything in your design?
No, we don't use specifically novel materials for space. We build autonomy and try to make these modules more autonomous by the day. So we deploy autonomy things, test them. We also we are trying to build a company, so we are trying to deploy it in mining caves, mineral exploration campaigns for surveys. So that has been a bit of the focus now. Maybe when we get to space, we need to, I mean, there's space is always challenging. There's more things you want to have LiDARs. We don't have LiDARs in space. Like you need to use space certified components, which are radars or other components. Like we don't have a 360 LiDAR yet. So all of those need novel materials to be discovered or created. People have to work on it if you really want these autonomies to go to space, right?
Thank you.
I just had a quick comment. We are obviously running late, but we have working lunch arranged today, so it should be here in maybe 10 minutes. So we can continue. There are 2 more presentations. I feel bad for the last presenter who's going to be delayed, but we do have a boxed lunch. So you can please bring your lunch in when it comes here, and we'll continue with the discussion. And Vivek, please stay back because it looks like there are more questions for you. You can grab a drink and then stay back. Lunch might be a little bit delayed, but I hope you can hold on to your hunger because we have 2 more presentations. And can we maybe hold on to, there are a lot of questions coming up, maybe just, after the presentations are over, can we please, go back to the presenters and ask the questions, okay? Thanks a lot.
Next speaker is here, Astha. They had the first space analog mission in Leh in November 2024, and it was all over in the news. So welcome, Astha.
Thank you. Maybe I'd like to show the video first. A very good afternoon, everyone. I know that most of you are hungry, but I'll just take a few minutes to take you through the analog missions. So my background is into space architecture and analog astronautics. I was in Canada handling the FMA station. This is a sneak peek into our world's biggest analog mission that happened last year. We had astronauts for Prashant Nehru, who stayed in our facility last year. Yes. Yep. So basically, it's very interesting to see a lot of geological presentations and on rovers. So I can say that we are the infrastructure foundation for all these missions to stimulate before we are launched in space. So today I'm going to explain about how we can use the analog platforms to validate platform before the planetary and the surface operations. Now, human space flight is entering into a very complex phase. We have these low Earth orbit missions. We have long duration space missions, for example, landing on the moon with the Chandrayaan and Artemis missions. And there is an increasing complexity across the life support systems, how the human will behave, because we only have less than 1,000 astronauts who have been to the space and less than 24 astronauts who have been onto the moon. So understanding the human behavior and predicting the human behavior for space missions is also a very crucial factor. Then habitat systems engineering. For example, what kind of life support system we will be carrying. All of this needs to be validated for a very long procedure while we are on the ground. And operations, autonomy, and comics. Also, the ground communication with the crew inside the habitat is also very important. And power, thermal, and resources. So reliable Earth-based validation before the mission deployment is crucial. And that is what we are trying to develop. Yeah. Moving next. I'll just use the keyboard. Yeah. Oh, laptop is hanged?
Laptop is not working.
Maybe we can restart. I think it's working. Yeah. Yeah. Okay. So when we talk about Indian spaceflight programs, we have Gaganyaan, Bharatiya Antariksh Station that ISRO is planning to launch. And also there will be a global shift towards the planetary missions. So it is so important to identify how are we going to do the whole planetary habitation on the moon surface. So let's say, for example, so we do a very rigorous process of understanding the landing systems. So let's say SpaceX is landing on the lunar surface. How the prehab structure, prehab habitat will be deployed from the SpaceX. How it will operate, how it will generate the power initially. What kind of manpower we will have on the moon to deploy the habitat. What will be the initial experiments that we'll be doing? How long the mission duration will be? What all we will be studying except collecting the samples. So there is a sequence of things that happen when we will land on the moon or even for the space. When we're talking about the space missions, we talk about pre-flight mission training, ascent, in orbit, docking, descent phase. So how the human and the habitat interaction happens, that is what we try to stimulate in our analog missions. And there's a lack of integrated testing platforms across the system. For example, in space testing is extremely high. We cannot send everything to space to test and then bring it back. Also, there's a limited iteration capability, and there's a high risk from unvalidated systems. So that is why analog plays a crucial role to test these systems before. Now, there are various types of analogs across the world. Planetary analogs, Arctic analogs, underwater analogs. The first one is from our mission. There's an underwater analog, polar ice, desert arid analogs, volcanic geological analogs. So what all these analogs actually do? So they understand, they do the space system validation. I'll explain you, for example, let's say we have a payload for, let's say microwave, as simple as that, which is going to be used in space. But we will run a multiple simulation in an analog environment and collect generated data, how that microwave is going to perform when it goes to space. So that is under the space system validation. Then we have the human isolation study, which is also very crucial because human factor is the critical, and we are spending billions of dollars into the infrastructure. But only through analogs we are generating the human data. For example, their biometric data collection, their HRV, sleep, stress, which help us to predict their performance in space. Then we have EVA simulations. EVA is mostly for the terrestrial EVA simulations. For example, this is also very similar to that of when we talk about space. So we do this, astronauts are doing this spacewalk. So they are mostly doing the habitat maintenance, some docking and rescheduling of the satellites. And when we talk about the planetary EVA simulations, then we talk about how their suits will behave, inflation, deflation, what kind of life support systems will go into that space suit, how far they will go from the habitat, how they will communicate to the habitat. So all of this operational protocol testing, crew training, integrated system testing, resource management, what the water supply. When we are doing analog mission, we are able to identify how much our water is being reused, how we can reuse that, resource management. So we do multiple testing in analog environments. So enable pre-mission testing under stimulated constraints is something which is very important. Now, 4 years back, I approached, when I moved back to India, I was in Vancouver before and Europe. And when I moved back to India, I just started studying the ISRO's Gaganyaan program. And earlier they had 3 crew seats in their program. And because my background is into space architecture, I started understanding that crew module. And we identified that only 2 persons can be the crew module instead of the 3. So we did a very intensive study on the anthropometric ergonomic study for them. This is a glimpse of it. As when we are flying, when the astronaut is flying to the space in microgravity, they have a complete different notion of their movement. So it is very important that whenever we are designing an analog habitat, we are integrating the human body performance in the space. So what will be the sagittal plane? What will be their angle? So for example, when an astronaut is wearing a space suit, how will be their angle of rotation, the movement in case of if there is an emergency in the ascent phase and they have to immediately approach they have to open a medical box, how they will do that with the gloves, with their proper suits. So all of these simulations can happen here. And that's what we did a study. This is the iteration of that. So we try to understand. So Gaganyaan mission is basically for 3 days. So we try to understand, okay, the astronauts will be wearing their full inflated suits. They will go to the space. The suits will deflate. They will be using the rehydration station. They will be doing some small experiments. How they will move inside that small capsule because the seats are not, the crew seats is not foldable. How they will access the space. So this is extremely important because it can also create a psychological constraint. So when we started ARCA, the first thing we started understanding was the human spaceflight missions, not only of ISRO's, but also what is happening in International Space Station. Now, when we say current ISS station, it is so clustered. It's a cluster of all electronics and everything moving about. So when we are staying for a long duration in that environment, that also creates a psychological impact. Now you see the EXIM space station, the VAST space station, the new stations that are coming, that are less in clusters. So that is how we started our studies. And this is the first mission. This is the first prototype that we built for India's first space analog mission. It's a small, it only has a crew capacity of 1 person. And we focused more on the anthropometric study, factors engineering, ergonomic study, EVA geosampling. We did this one in Ladakh. And cognition protocol, the analog astronaut was also collecting his own blood samples, their cortisol sample, the saliva sample, and we did a very in-depth study of his performance into a small capsule. This mission was for 21 days. It's the longest analog mission till date in India. And based on that, we built a prototype. Because personally, we believe that if we cannot build it, there's no point of designing. So we should be able to execute whatever we are putting our researches into. So this is a Teflon-based structure. This structure is completely designed, built, fabricated at our studio. And for this mission, we had partnered with ISRO. I think many of you might have seen this one with ISRO and IIT Bombay, where ISRO helped us with the setting up the protocols for the human biometric data collection system, and whereas IIT Bombay helped us with the psychological evaluation and the crew training and the analog astronaut selection for the mission. And our ACA's purpose was to understand the habitability and its survivability and the structural performance and the human dynamics into a small capsule. So these are some of the pictures from the first mission in 2020. This happened in 2024. You can see we are doing some ECG, and we also developed a special circadian lighting system for this, which is basically mimic of how the sunlight, the sunrise from the sunrises to sunset. So we mimic that opacity of light for the space, and we had developed this one. And you can see everything is completely done in-house. We were in the news for this. We published some papers also on it. And so after that, we were like, how do we integrate this? When we were working on this project, that time there was no Bharatiya Antariksh Station. This is completely our own design structure. So we went to ISRO and we proposed that, we have been doing some designing and we built a small prototype, and if we have to integrate with Bharatiya Antariksh Station, how will that work? And this is a small concept design for that. But we also published a paper on this one at International Conference on Environmental Space Systems at Boston in US. So the process is very important. Now, okay, inflatable habitat is there, but how it will inflate from the crew module, how the interior systems will inflate, how we will place the systems inside. For example, ISPR racks, how they will go. This all is very important to study. So we do a lot of, we do almost hundreds of sketches on ground before we actually start building up something. So this was mostly for the functional zoning and anthropometric environment mapping. And after our, I personally spent 8-9 years into studying space architecture, and now we understood that this is a time now, this is the right time to build our permanent analog facility. And this is the only first part of our permanent analog facility. We presented this facility in the world's biggest analog mission last year with 17 other analog habitats across the globe. For this, we partner with the various institutions, for example, IIT Madras, IIT Hyderabad, PRL, Nirma University, Government Sahas Schoolie, Salem, Government Sahas Schoolie, Ooty, Kutch University, Mycobi, some very established engineering companies. And this is a completely off-grid habitat. It can go anywhere in the world. It can go in Antarctica, Ladakh, anywhere. And we can run the missions from 2 days to 365 days. We just need to do a resupply of water and the food. And the amazing thing about this, I will explain in the future and the coming slides. So you can see we presented India over here. I think there is a point. Yes, we presented India over here. And these are all the other analog habitats that took part into it. So there was an international protocol developed. For example, now all of these analog habitats are operating. I'll tell you something. NASA also has its astronauts trained at analog habitats, for example, in Nemo, in MDRS station, in Iceland, before they actually fly for space. Even ESA does a lot of analog habitat studies. But all of these analogs were operating on a different scale with a different validation systems. So there's an organization called World's Biggest Analog Organization, where all of these directors and experts from NASA, Hera Habitat, from ESA, they all sat together and they put up a standards to how to conduct the analogs as per the international standards. And there was a unified mission that happened last year in the month of August, where for 2 weeks, where all these habitats was doing the exactly same research with exactly same outcome, with exactly same analog astronaut crew selection. And with that, we got our validation. So we are a certified analog mission service provider. You can see this is our seal. So if anybody says on what basis you have built an analog, we can say that it is as per the international standards. And they said there was a rigorous process to get this validated. It was a 2-year of a process where first we had to understand what kind of ethical clearances we need when we are testing on the human, what all we can do, what are our limitations, how we select our crew composition and dynamic study. We had to take a personality test before we put all the crew together. Training and mission simulation capabilities, 4 research domains in analog missions. One of the studies that we did was also how does microbes behave in the controlled environment, target study. There we opened up the applications for different experiments. And what should be our life support system capabilities. So every think, for example, any habitat sensors that we have used inside, even for temperature sensor or humidity sensor, all of these specifications we had to submit, and two analog astronauts from the who were trained from the WBA came and they validated our systems. And that is where the Papanaya sir was also part of this. So this is the interior layout of, it can accommodate 4 crew members at a time. It has a galley. Galley is like the space kitchen, I will say. We completely use freeze-dried food. There is no cooking inside the habitat. We have a small lab and operations module and utility module. And this year and next year, we are expanding into much more bigger modules. This is more interior picture, so you can see our crew quarters. Now, also privacy is one of the big problems in space because they don't have a privacy. So we made sure that all of these standards are also aligned to the International Space Station, and it also aligns to the future Bharatiya Antariksh station. And it supports the cognitive optimization, environment personalization. Then this is a food production module, microgravity. We are trying to develop a complete hydroponic aquaponic system for space. This is our galley module, lab and operation, hygiene, and analog module. One of the also problems that we face, because there's a lot of geologists here, so I'll say, in the Apollo missions also, when the astronauts came back to the lunar landing module, a lot of dust, silica dust came inside that module, and then it exploded some of their electronic system. So we also face a similar thing in our analog missions. When the crew is coming back from the EVA, they bring a lot of dust inside the habitat, and it's very difficult to remove that because when we open the door of our habitat, even at the outside temperature and it's windy, it brings even more dust inside. So this is something, a real scale problem that we also have. So that's why we have an air shower system which removes the dust so that the pressure is more inside than outside, so there is no dust coming inside. So we are trying to go, of course, I've not reached that actual space level, but we are trying through trials and errors as close as we can go to. It's fully off-grid functional. It has a 45 kilowatt solar power capacity. There is no external electric supply. And even in current missions, we have more electricity available than we need. So it's even overperforming. We have an HVAC system, heating, cooling, everything, integrated surveillance and remote access. We can see from remotely extreme temperature to extreme low temperature support and faster deployment. We built this whole habitat in 5 weeks. So in 1 year, we can build 8 habitats. So one system capable to adapt to multiple analog environments with limited external dependencies. One of the very interesting experiment that this was an experiment, I will say, for our future expansion was this. Our partner, government Sarkuli Uti, Professor Venugopal, helped us to procure this olivine simulant from Tamil Nadu, and with lime we put it into and we 3D printed with. This was a basically study on understanding how does the radiation on the Earth and the Mars, and how does this olivine based simulant is performing. And also, if we are 3D printing on the lunar surface, on the Mars surface in future, how we will deploy the robotics for that, and what will be the initial form of construction would look like. And if we were to stimulate this facility here, then what kind of operations do we need to have? So it's a very pilot-based study, I will say. I don't know how this news guys catch up. Then the rover was provided with, from IIT Madras. So I think what exactly Uncharted AI explained about their robotic operations, we try to simulate this thing here. So this rover was completely running with on coding system. So they trained our analog astronauts. We did a mapping on. So we did this whole mission at a place called Layari River section in Nakhatrana area in Kutch area, where they actually have this NASA blueberries which are rich in iron content, which is actually found on there. So PRL help us to identify some of the locations where we can do the sample collection, and we perform the whole simulation that okay, the rover is being deployed from the habitat. Habitat is the landing module. It's going at this distance. How are we communicating to it? How it is collecting the sample, bringing back, and how we will store that sample inside the habitat without giving an exposure. So this was also a simulation study, landing and autonomous remote deployment to commissioning and system initiation. We mapped the terrain, travel path and environment to autonomous transfers to the target, robotic arm deployment, geological sample collection. This is not my technology development, this is from IIT Madras. And IIT Hyderabad also provided us with the Mars battery. they set up some protocols to test it in this analog environment. So the idea is that it's analog is not just for the astronaut. It is also, it's an ecosystem of different disciplines coming together and trying to simulate the real life scenario. This is something that is our technology development. So we developed our own telemetry digital twin system. What does it do? It collects the data of the habitat for 24 hours. So we developed our own sensors, habitat sensors inside and outside of the habitat, which would tell us the pressure, humidity, temperature, oxygen, CO2, O2, all of these things. And then we can see, this is a screen which is there inside the habitat right now, and it gives us a live monitoring of our habitat performance. And this is our portable mission control system. So we can see the data of our habitat and the data of our crew, like what is the sleep of the crew, how much steps he have done from anywhere in the world. And now we are even advancing this more this year. And this is the data we collected. We are working on segregation. So now what happens? The data comes at every minute. So we have to segregate that, and we are working on a simulation engine which will tell us the prediction. So it will tell us that, okay, your crew number 2 is having a sleep fatigue, you might want to change the schedule. You are running low on the power generation, you might want to change your, you might want to turn off a habitat, or in case there's a fire or smoke, it will give us the warnings. Now this kind of automation is very important when we're looking at planetary habitats or space habitats. Here's some of the pictures from the WBA mission. This is the 3D printer machine, the target study, and some more. Again, so in just 2 years and 3 months, we developed, this was the first habitat. Nobody has seen this, it's not in the news. We did an all-female crew mission in Kutch. I personally, we were always debating to either to go for Ladakh or Kutch, but we came to conclusion that Kutch is more preferable for us because we can run the missions throughout the year, and we can also scale it rapidly. And Kutch is also a scientific analog site. I saw some presentations before, and NASA and PRL and many other institutions have already been supporting for the Kutch analog site. This was an all-female crew mission. I personally feel that there should be also women astronauts, so I try to encourage women in space this time. This is the Ladakh human analog mission, first one, where we did the 8 critical research areas. This is from the last mission, where we did 16 critical research areas. We got ourselves validated, and this year we already finished 9 missions where we had academians and students, especially university students who are in their PhDs and masters, who stayed in our facility for a period of 7 days, and they conducted different kinds of studies. And the one is starting from today, where we have 3 females who are going to stay in our habitat and do the research. So it's running very, very successful. Now, how do we validate? This is very important. See, analog habitat is not just where you put up a good-looking structure and you say, and where the crew is staying inside, sleeping and eating. That is not an analog. Analog has to validate the systems. That is extremely crucial. So how do we do that? So this is the system refining loop. Let's say, for example, we develop a system. Let's say this is our own example that I will try to say. So we develop the circadian lighting, which is the lighting used in the space station right now. So we develop a system. We stimulate that in our analog simulation. So it was deployed in the lab mission, and again we developed a full scale of it in our current container that you saw, current habitat that you saw. Then we assess the performance. So then we also assess the performance by intensity accuracies. For example, how is the astronaut able to sleep in this blue shade? How is the red tone working out? Is the astronaut able to mimic the whole sunrise, sunset, 24 hours light cycle inside that? So we do we collect we do their cognitive test to analyze this lighting. Then meet up to flight readiness standards. This is where the most space agency come into the picture. Even when a Bharatiya initiative will be developed, they will need the circadian lighting. When right now ISS has, even the EXAM space station, all of these are going to have circadian. This is just circadian lighting is just one example of the whole thing, and it will go validated to government or space agencies. And then we reached our TRL 7 for this. Now we are working on a small prototype that we can send in as a payload in the Bharatiya station. This is our fabrication facility. We have almost a 30,000 square feet of the facility. Anything that you saw was completely built in-house. Our team, we have a very huge team who are some different backgrounds, who are from Emirates Systems Engineer, electricals, mechanical engineers. And this is where our site is. It's in Dholavira. One of the reasons of also going here because, and these are all the scientific analog sites around our facility in the area of 200 kilometers. So in future, if you are putting an ISRU facility, that it will be easier for us to procure the simulants. And also we have our own industry here. So it is only 2 hours in case of any failure, operations requirement, emergency requirement, we can evacuate the queue. For example, recently there was a severe thunderstorm in Kutch area. It was in summertime, which is completely unexpected. So we had to evacuate the queue. So, and also it has this Harappan civilization. This was the first civilization on the earth. When we are, as a space architect, when we are trying to develop our conceptual studies on how the first civilization will happen on the moon, it just gives us a very stimulating study. And also it has the fossil parks from the time of dinosaurs. So it's a very scientific analog site. And also it gives like a moonland feeling. You feel like you're on the moon. This is our team. We have a big team. Some are advisors, some are full-time with us. So till now we have done our own 4 analog missions, in-house 4 analog missions. We have done 9 civilian missions, which is open for the students. 106 days we have run the mission throughout. 14 mission partnerships and 18 critical research. These are some of our partners. We have a massive industry network by now. Now, because I see that mostly today it's all academians, I thought why not we add how industry and academia can collaborate with us. So we are an end-to-end analog mission service provider. We can support in your academic research, and we can run a mission from 1 to 120 days. Who all can participate? Anyone, undergraduates, postgraduates, masters, doctor, faculty, early career advancement, any can participate. And this is something for open for all: aerospace, mechanical, robotics, life science, psychology, human factors, environmental, earth science, architecture, space architecture, computer system, astrophysics, biochemistry. All of them can be a part of such a mission, because even right now when we have a crew, they're all coming from different backgrounds. And space architecture or any habitation, when we talk about it's a combination of different disciplines coming together. This is already being mentioned with. So I feel that the future of human spaceflight depends not only on the launch capability, but how rigorously we validate life beyond Earth, on Earth.
Thank you, Asta.
Thank you, everyone.
It's a wonderful talk, and I am sure there are a lot of questions. But since Siddharth is waiting, I thought, and it's lunchtime, we'll just take the questions after.
Yeah, and in case somebody is very hungry, we do have the boxes outside. You can bring the boxes in here, but we'll get started because the next speaker is supposedly, he's traveling. So he's waiting somewhere. So we'll just get him started. But the boxes are right here. I think there are volunteers out here with coupons.
Hi, good afternoon. Can you hear me?
Yeah, so next speaker, Siddharth. So first thing I must say is that Siddharth, the whole thing started because Siddharth wrote to me a few months back introducing Martin, and that's how actually the whole thing started. So thanks a ton, Siddharth. So all this is because of your email. So Siddharth Pandey have been at various places as in NASA as a postdoc, as in Australia, known him for very many years. Currently here today, he's as from Protoplanet Private Limited, a startup that he has founded. So Siddharth, take it away.
Thank you so much. Is my screen visible?
Yes, Siddharth, please. Go on.
Awesome. Thank you so much. I'm very conscious of time, and I'm aware that I'm in between hungry people and lunch. So I will try my level best to stay on time. And I'm also being ambitious to fit in 2 talks in 1 slot. So bear with me. I will try not to rush, but at the same time, to this Mars Science Workshop audience, I wanted to convey 2 areas where we can help. One is the critical area of sample collection, which as I understand is critical for upcoming Mars surface missions. So I'll talk about completing through a journey of my experience and what are areas that would be important to hear. And the second is through the lens of terrestrial analogs, talking through some of our experience supporting science teams, engineering teams in terrestrial analog environments. All right, can someone please confirm they can see the second slide?
Confirm.
Thank you. So I'm able to talk with some confidence on sample collection technologies. I've spent about 3 to 4 years collectively over a 14-15 year career helping develop sample collection technologies for various sorts of missions. Starting with work on pneumatic systems that essentially use pressurized gas to collect samples. Our technology has been tested on the lunar surface as part of the Lunar Eclipse mission in 2024. And it's also part of the sample collection payload that will be flying on Japan's MMX mission, the Martian Moon Explorer. Subsequent to that, I have tried and understand the environmental effects on systems, particularly for Venus. One of the technology concepts that we developed was a high temperature sample collection system for Venus. And that has its own share of challenges that I will not go into today. In addition to that, as a postdoc at JPL, was involved with the development of plume ice collector for a Enceladus fly-through mission, wherein the spacecraft literally flies through geysers, coming out from the polar regions of the Enceladus moon. So another very different, unique set of challenges for collectors. And lastly, recently was part of the team that developed the scoop arm arrangement for the Australian Space Agency's lunar rover as well. So that is just a collection of different missions that I was involved with regards to collecting samples. Now, talking about Mars, this is an image that shows how on Earth you would try and collect subsurface samples. That's a picture of Dr. Steve Hobbs on our expedition last year in Ladakh, wherein he's literally using a spade to dig through about 2 to 3 feet of soil to get to permafrost, which is buried ice in the Soker area. And that's how we would do it on Earth. But on Mars, challenges are obviously very, very different. You're looking at robotic and operations-based technologies that would work without human intervention. And Ritu ma'am, talked extensively about how remote operations will decide technologies that eventually get integrated into spacecrafts that reach the Martian surface. I'll spend a little bit of time talking about the advantages of sample collection, although I'm fairly confident that most of you are convinced of surface missions. So, of course, sample collection from the surface allows direct examination of the samples. It allows us to get insights that are not possible alone with remote sensing. And mainly when you're looking at trying to study complex organic molecules, trying to look for biosignatures and look at the subsurface, this is something that is not entirely possible, through non-contact or remote sensing means. Preservation of sample integrity. So if you're trying to collect, data that you would like to understand internal structures, this is something, again, that is not possible through remote sensing. And lastly, the unknown unknowns. And this has been a theme in Mars exploration where we learn of things that we are not sure of. And those are the kind of discoveries that sample collection opens the doors to. Surface mission goals are also achieved through sample collection. And we've seen this in past missions. We've seen how understanding the geological history of Mars has been enabled by cameras like the Mali camera on Curiosity that was able to capture high-res images, providing samples to APXS instruments. All of this requires sample collection. When we're looking at Martian habitability, instruments like the SAM has helped understand the habitability potential of the Martian surface. And also, unfolding the climate history, collecting samples to understand what ancient atmospheres were like and what was the impact of the environment on the surface is something that has been, decoded through sample collection. And lastly, of course, focusing on human exploration, instruments like MEDA have helped collect data from the surface that help us understand and characterize the Martian environment. Now, I will talk a little bit about the challenges that are associated with sample collection or planetary drilling. One of the main things that makes it really hard to design a sample collector is the uncertainty involved with the geotechnical data of the material that one has to drill through. So the biggest challenge is that you have to build a tool that is able to drill through brittle, soft material and also be able to handle sticky, ice-cemented hard material. And that's challenging because on Earth, based off what you're trying to drill into, whether it's wood or cement, you would choose very different tools. And this is the fundamental reason why drilling is hard or achieving subsurface samples is hard, because whatever you design has to be able to work in a variety of different possibilities. Then there's, of course, the traditional challenge of trying to fit something in a very small space that does not weigh too much and doesn't take too much power. So drills that would normally on Earth take hundreds of watts or thousands of watts have to operate in tens of watts. In addition, there's the environment. Mars is no different. Working in low temperatures, high radiation environments, high dust environments, all of these things make it really hard to do complex mechanisms. And of course, most of the places we land, Mars included, don't have enough gravity. So the weight on bit is limited. So one has to put more force to be able to go deeper. And one has to then rely on things like percussive drilling, which is hammering. And all of that requires more power and is also complex. The last point, of course, is redundancy. It takes years and years of development of such systems. And that is something that affects the timelines in terms of finalizing systems. And each and every motor that is part of such systems adds a potential point of failure. So this is why it's important for the community to understand that for a mission that has to fly in 10 to 12 years, development work should have started yesterday. It takes about 7 to 8 years of time to develop customized drills for missions. This is a table of summarizing the different kinds of tools that have been used to collect samples. As you can see, it's not a very long list. Right from the late 70s and all the way down to the current time, there's only been so many inventions that have happened. So you actually are limited by choice. You normally have either a scoop, an auger, or a core-based drill, and you have impactors that are being used by the Japanese in their missions to collect samples. A scoop is essentially a robotic arm with a scoop at the end of it. These are images from the Phoenix mission, wherein you're essentially collecting, literally scooping available loose soil from the top surface. You can do some amount of scraping, but as was found by the Phoenix mission, as soon as you start hitting hard ice, it's very hard to penetrate it. Next comes drilling. And even on the surface of Mars, we've only been able to drill until several inches, nowhere close to the meter depth, target depth that is normally needed by the scientific community. So the drilling operations have been fairly successful, both in Curiosity and in Perseverance. But these are very advanced set of instruments that have to actually provide samples to a range of different scientific instruments. So it has taken several years of iterations to reach the level of systems that have to be deployed to collect samples. I mentioned pneumatics. So I'm a fan of pneumatics because you're essentially using pressurized gas, which is inert and doesn't chemically react with your target samples, but it removes the amount of mechanisms that are required to transport the cuttings or the samples that you have collected. It also has its share of limitations. You're not able to drill. You're essentially transporting material that is available on the surface. But then again, there are smart ways in which you can use pneumatics to move samples from one place to the other. And this was successfully done in the Lunar Eclipse mission, or the mission that landed as part of Firefly on the lunar surface and is part of the Japanese MMX mission as well. I'll talk a little bit about the relevant discussion themes of this conference. If you're trying to build a strategy to collect samples at an ancient hydrothermal vent field, it is important to ensure that whatever collection methods are used, we focus on preserving stratigraphy. And this is something that is really, really hard. It actually limits the number of options that are available to carefully, collect the sample. Some of the options that are mentioned here are, again, very early level kind of thoughts from my end. but we are basically looking at options that minimize frictional heating, vibration that damage some of the delicate opaline silica samples that we are looking to collect. We can think about using ultrasonics, high frequency vibrations instead of high torque, options that are ideal for brittle materials that have low weight on bit as well. One can also think about using adhesives that would essentially have material that sticks. So if you're looking at surface crust material or potential microbial mat kind of material, that can be used to stick to a collector surface. And lastly, if you're looking at volatiles, that is the hard one, but essentially having capsules that can essentially capture sublimed material that comes out from the volatiles and then traps them. What makes it even further challenging is if you're trying to do any form of biosignature signature detection, the constraints become harder because firstly, you cannot use too much of heat. You would want to prevent any chemical alteration of the samples. Planetary protection requirements are much harder. So cleaning of such systems is very, very challenging, and ensuring there's no forward contamination is going to be really hard. I mentioned two challenges that have happened in the Mars missions. The first one was what is called the Rubian incident. So Rubian was a rock that the Perseverance rover tried to drill through. And from the outside, it looked like a very hard rock, but actually that was very, very brittle and soft from the inside. So when they used ultrasonics to collect the samples, expecting that they should be able to drill through it, it actually damaged all the samples on the inside. It pulverized the sample completely. So that was an example of how the outside surface characteristics of the target rock sample could actually, fool you, and you wouldn't realize what the internal material is like. So that is a challenge that's hard to prepare for, but it actually requires operation teams to be able to have those alternative options to collect samples in case if they encounter material that is softer than what was expected. The other challenge that happened was with the Curiosity drill, wherein one of the motors actually had a short circuiting, and the percussive force was not strong enough. So the robotic arms force was used to collect the samples as well. So these are the kind of challenges that have been faced in Mars missions that make it really, really hard. Added to that, there is also the complexity of the three tasks, which is sample acquisition, processing, and instrument delivery. So I'll walk through this little text-heavy chart. On the left side, you will see a table from a paper, which explains how the different kinds of samples are categorized in terms of what sort of information do they hold, whether that's biogenic or about the atmosphere, the lithosphere, and whether it's to understand from a resource perspective. So normally there is a chart of material that is prepared for each site that gives an idea of what kind of samples are present and what kind of information do they hold. Next, when you have your suite of instruments that are on board the rover or the lander, each of them have their own sample requirements, whether it is loose material or pulverized, dust, fine material. So all of those instruments have their own different requirements for what samples they need to be given. And then on the top right side, you will see how all of this process needs to be automated, wherein once the sample has been collected, it has to be firstly processed, which basically means it has to go through a sieving process or a crushing process to get the sample into the desired particle size or distribution for the instruments. And then it has to be carefully passed on to the instruments, whether that's LIBS or your, the imaging instruments and whatnot. So all of these procedures are complex. So depending on the complexity of the mission and the complexity of the science goals, the drilling process also becomes challenging. That ends my first half of the talk. I'll quickly talk through analogs and the value that they add to the community. And I'm particularly speaking to the scientific community, as well as the community of people involved in mission formation, whether that's at space agencies or other institutions. So Asta has already given a talk. I will not repeat a lot of her points in interest of time. But I think it's fair to say that analogs are not to replace lab work. They complement lab work. They serve the purpose of validating a system in a naturally occurring environment. India has been mentioned, today, as well as I think Yamini mentioned it 2 days ago. We have a suite of high value analog sites, and each of these sites has something very different to offer to the different teams that are working in planetary sciences. And we're obviously aware of upcoming missions and what role these analogs can play to systematically help improve our science objectives, hypothesis, all the way going to validating instruments in the field, as well as operations. That is something that does not get spoken much about, but in time critical missions, simulating environments that help us test out the operational protocol is something that we have recently done with the Human Spaceflight Center, and there's a lot of learnings that have come out of that. So I will not go into a lot of detail. My slides are already there with the conference, but essentially the imperative is to reduce risk, mature technology, validate operational concepts, to build scientific contextualization. This is an important point because, as I understand, within the planetary science community, there's very few people who understand biology and biological processes. So analogs are perfect places where they can actually see how both the geological and biological processes are interacting. And this is something that we've seen contribute to the development of interdisciplinary teams. It helps us provide that context and also helps us understand how do you interpret data that is coming back from these missions, where teams can get a multidimensional understanding of how that particular rock or that particular geological feature might have been formed. It's important for us to be able to understand that on Earth so that it gives us a sense of an overall understanding of the picture. And lastly, I use the word crew training, but aside from human space program, analogs are a perfect place for scientists from different disciplines, engineers and instrument designers to actually work together to understand how complex surface operations can be undertaken. In terms of robotic systems development, I think some of this has already been covered by the Uncharted talk and others, is that you can test out mobility, navigation in naturally occurring slopes, distribution of rocks. We've got locations like Ladakh and Lunar, which is a basalt impact crater that allow us to do these kind of tests. Testing out instruments in the field and integrating mission simulations. We've obviously spoken a bit about the different locations in our country. Our team has been focused in Ladakh since 2016 in different affiliations and capacities. I've been involved since 2016 in coordinating some of these analog expeditions. And Ladakh particularly has been interesting because it brings together a very wide variety of scientists. It's an early Mars analog because of its high altitude, UV radiation and cold environment, and the presence of extreme locations like hot springs with boron in it. We've been working with Martin, Sudha, Dr. Mukund and others at BSIP for all these years to help understand what exploration of hot spring sites actually means, and how does that knowledge that can be converted both for the origin of life community, but also from the point of view of future robotic missions. The presence of permafrost is very, very unique. There's very few places on our planet where you have access to permafrost, and that's something that has been an area of constant interest. And in addition to that, we've held some preliminary visits to locations like Lunar, which is a basalt impact crater, one of the very few on our planet that are accessible. And we've drawn parallels with understanding how Jezero crater might have formed, as well as how life might be trapped in the inner and outer ejecta, as well as the gullies of the crater. Kutch has been mentioned before, again, very high value site, as well as ice-free regions of Antarctica around the Indian station, Bharti station in Larsman Hills, offer opportunities to do more analog work. Won't go into too much detail, but we have been trying to map the different technology tests and mission relevance to different analog locations on our planet. Ladakh has been our first location, but then there's other locations where site characterization, pathfinding trips will be conducted over the next few years. So the approach we've taken to analogs is not particularly for infrastructure building, but it's actually the other way around, wherein we have spent a lot of time understanding and characterizing an environment. and breaking down what that has to offer to the community of scientists, researchers, engineers, and mission formation people, in agencies. Over the last decade, we've had about 8 expeditions that we've conducted in Ladakh. And with each expedition, our understanding of the region has increased, and we've been able to build confidence in terms of what sort of long duration studies, can be conducted there. The establishment of the Hope Station last year in collaboration with the Human Spaceflight Center at ISRO and the Mars Society in US and Australia that manages stations in the Arctic as well as in the US has been a monumental achievement for us. It was built on the back of 9 years of experience working at the location. And we just a few weeks back completed the Mitra mission, which was a human behavior performance study with the astronaut team and the engineers of Human Spaceflight Center. So I don't want to go into repeating some of the points, but Analogs has something to offer for STEM, for research and scientific community building. And we've taken a structured approach over the last 10 years to build that rationale, working both at the grassroots level with students, all the way up to working with contributions to space science roadmaps that have been received at the Space Science Office at ISRO as well. And along the way, there have been a lot of tangible and intangible outcomes. For instance, the number of students that we have tracked that have gone through over 130 students, and out of which about 10 I have identified have actually made career changes in their lives and decided to dedicate their careers to astrobiology and planetary sciences. So those are the kind of things that we look out for. And of course, research has played a strong role, with most expeditions leading to research output that we hold very, very strongly, that the outcome of each expedition should lead to peer-reviewed journal publications. Some of our work has been cited. The work that was conducted by our team, including Dr. Sudha Rajamani's team, was actually cited by Dave Dima in a paper in 2021 in Life. That has actually helped us try to map out how the work that we've been conducting has put Ladakh on the map of the community, scientific community. These are just some snapshots of expeditions in the past where the work essentially involves characterizing lakes, Mars analog lakes, field training for students, as well as subsurface, mapping, permafrost mapping using ground penetrating radar. It also helps with hypothesis building. So on the left, you see a dust devil picture. And this was in 2016, a group of planetary scientists observed that. And a discussion took place that eventually materialized into a Venus paper, wherein they spoke about how dust devils might have played a role in the transport of salt deposits from lakes in early Venus environment when it was habitable, might have been habitable. And that's something that you cannot conjure when you're in a conference. So analogs play that role of helping inspire and motivate hypothesis-driven discussions. Going all the way to the right, where we've been collaborating with Dr. Javier's team, and they are working on developing a payload for the Mars, European Mars mission, ExoMars. Student rover teams, again, very important for students to be working in these kind of conditions to appreciate the effect of dust and static, and planning and preparing for things breaking down. There's intangible, benefits of doing this work in such a remote setting versus doing it, in their campuses. And last year, we conducted the Spaceward Bound expedition after almost 9 years that brought together scientists from Europe, Australia, US, India, together to continue exploring work in Ladakh. Won't go into too much detail, but the work essentially, is involved with doing some robotic experiments, building in some human research that started last year with Dr. Anu from University of Malta, and also working through microbial, sample collection and geothermal work as well. So a lot of the analog work actually starts with interdisciplinary teams planning, looking at maps, sitting together, scheduling, and very similar to how Mars missions would be formulated and are probably already happening in India, where you have people coming from different backgrounds and disciplines together charting out what kind of work needs to happen. And each night, sitting down and then understanding the data that has been captured in the day to help plan and reiterate, for the next day. The this is Dr. Steve Hobbs with a small A5 rover that he brought into Ladakh last year and tested it. It gives us the opportunity to do these small mobile portable tests to build instruments that could, potentially piggyback one day on larger missions. Snapshots of scientists working in the field. And yeah, there's some more photographs from some of our expeditions. And we set up Himalayan Outpost for Planetary Exploration, or HOPE. And it was a culmination of all the requirements that we received from scientists that had been working in Ladakh since 2016. And one of the main ones was essentially setting up an outpost that allows long duration experiments, as well as capturing of weather data that they wanted to have, like long periods of data collection from the location, specifically Sokar, which is where we are set up. In addition to that, the Human Spaceflight Center is interested in understanding the impact of that high altitude environment on the human body. So we've essentially completed the 10-day isolation study, wherein we had 2 analog volunteers who stayed inside, and there was a lot of physiological and psychological monitoring that was led by teams from IIT Bombay, IIT Hyderabad, IST Trivandrum, and University of Malta. So our approach is to first help build the case and the rationale behind analogs, and then slowly and steadily build infrastructure to support those tests. So that's the approach that we have taken. This was the visualization of what the station was to look like. And this was the station that we built and commissioned it last year. So not too far away from what the visualization was. And the main aim is, of course, to validate crucial technologies. We want to build technology and infrastructure based on the immediate needs of the space program. The approach is to first understand that, work closely with the stakeholders, and then proceed with setting up infrastructure. And this is my last slide, essentially working with ISRO on human behavioral performance. So in the middle of winter, our team was involved with taking up the astronaut team as well as human crew members. And one of the things that we tested out that might be relevant to this audience is how communications and operation protocol can be established, particularly in distributed teams. So we had teams that were simulating mission control, and we had 2 separate teams that had been deployed, in Ladakh, and laying out the communication data infrastructure and setting up the activities is something that was super interesting to understand how we are helping prepare, the upcoming both flight and ground crews to be able to practice some of their communication protocol to support some of the upcoming missions. So that was my time. Sorry for going slightly over. And I thank the conference for giving the opportunity to talk about this.
Thank you, Siddharth.
A quick question for Siddharth.
Yes, please.
Okay, yeah, Yamini.
Hi, Siddharth. Thank you for the amazing talk. I think my question is pretty naive, and probably one question for you and one question for the team from the Hope Hill, who spoke about all these structures. First question is it easier to drill down versus horizontally? So vertical drilling versus horizontal drilling, is it in space, it doesn't matter, or whether on Earth also it doesn't matter? I just wanted to know how scientifically or engineering technology, is it difficult to drill down versus horizontally in space?
So the answer is depends how much we're trying to drill and what are we drilling into. So if it is considered
both are same.
If both are same, downwards is better because you can then utilize weight on bit. So essentially, the weight of the rover or lander can be utilized to force downwards and work against, essentially use the weight to counter the force required to drill into. So that would make it better to do vertical.
Okay, thank you.
Questions for Asta? Oh, there was something. Oh.
From before.
Oh, okay. Thank you. Yeah. Thank you, Asta.
So yeah, Siva, thanks a lot for staying up, and sacrificing lunch literally. And so I hope you'll be able to continue to be part of the discussion session, which we will start in maybe half an hour from now. If not, we'll let you know what happens.
Thank you, everyone.
Okay, so that brings us to the end of all the presentations, and I'm really sorry that we're running about 40 minutes behind schedule. So we'll quickly go out and have lunch. Those of you who haven't, I mean, if somebody wants a second, that's okay. So let's do that, and after that we'll convene here and maybe go back to the chalkboard and see what we can put together. That's the goal. And for the online audience, the Teams link is going to be live. So if you are interested, please stay back.